Before cities cast their glow across the earth, before the hum of engines filled the air, there was only darkness and the endless dance of light above. In that ancient silence, when the world was young and wild, our ancestors lifted their eyes to drink from the well of night. They saw not distant suns burning across impossible reaches of space, but the very breath of gods, the scattered campfires of the dead, the silver roads that spirits walked between worlds. Each pinprick of light held a story, each constellation a map to meaning in the vast uncertainty of existence. They did not know that the stars they gazed upon had already died, that the light touching their eyes was ancient beyond measure, carrying whispers from a time before their civilizations were even dreams. They saw the stars as eternal witnesses, unchanging guardians in the dome of night, never knowing they were looking backward through time itself, seeing the universe not as it was but as it had been, long before the first human heart ever wondered at the mystery above. If this journey into history moves you, take a moment to like, share, and subscribe. Let timeless stories find new hearts, just like yours. In the beginning there was wonder. Long before the first words were carved into stone, or the first cities rose from fertile river valleys, humans looked up at the night sky and felt something profound stir within their souls. This was not merely curiosity, but a deeper recognition, a sense that the scattered lights above held answers to questions they had not yet learned to ask. The earliest humans were nomads, following herds across vast grasslands and through forests that stretched beyond the horizon. They carried no maps, no compasses, no instruments of navigation save for the celestial dome that wheeled overhead each night. In those dark hours when the world seemed vast and unknowable, the stars became their most trusted companions. They noticed patterns in the chaos of light. Certain stars appeared together, forming shapes that the human mind, always hungry for meaning, interpreted as familiar forms. Here was a great hunter. There a woman pouring water from an eternal jug, and beyond them a bear walking endlessly around a point of light that never moved. These were humanity's first maps, written not on parchment, but across the black canvas of space. The stars told them when to migrate, when to plant, when to harvest, when to prepare for the long sleep of winter. They marked the passage of time in ways that daily rhythms could not capture, revealing the great cycles that governed all life on Earth. A particular star rising just before dawn might signal the coming of spring floods, while another pattern might warn of the approach of the dry season. But the stars offered more than mere practical guidance. They provided a sense of constancy in a world of constant change. While seasons shifted, animals migrated, and landscapes transformed, the stars remained faithful. Night after night they appeared in their appointed places, following paths as reliable as the rising sun. To early humans, this suggested a universe governed by order rather than chaos, by purpose rather than random chance. Around campfires that flickered like terrestrial stars, the first storytellers began to weave tales about the lights above. They spoke of heroes placed among the stars as rewards for great deeds, of gods who walked the silver paths between worlds, of ancient battles whose outcomes were written in the very structure of the heavens. These stories served multiple purposes. They helped people remember the star patterns, they provided explanations for natural phenomena, and they connected earthbound humans to something larger than themselves. The moon, with its changing face and obvious connection to the tides and the rhythms of life, became a central character in these early cosmologies. Its phases provided humanity's first calendar, dividing the passage of time into manageable units. Women noticed the connection between lunar cycles and their own biological rhythms, while hunters observed how the moon's light affected the behavior of nocturnal prey. As generations passed, the accumulated wisdom of star-watching became the foundation of human culture. The position of stars at a person's birth was thought to influence their character and destiny. Seasonal festivals were timed to coincide with important celestial events. The dead were sometimes oriented towards significant stars, suggesting beliefs about the journey of souls after death. Yet even in these earliest times, careful observers began to notice anomalies in the celestial order. While most stars held their positions relative to one another, a few wandered across the sky in complex patterns. These wandering stars, planets, though they would not be understood as such for millennia, seemed to follow their own mysterious purposes. They became associated with the most powerful gods, their movements interpreted as divine messages or warnings. The brightest of these wanderers was the morning and evening star, appearing sometimes before dawn and sometimes after sunset. Many cultures initially believed these were two different celestial beings, not realizing they were observing the same planet Venus at different points in its orbit. This planet became associated with love, beauty, and the mysterious forces that governed human relationships. Another wanderer, Mars, caught attention for its distinctive red colour and its dramatic changes in brightness as it moved through its orbit. When it appeared bright and red, it was often interpreted as a harbinger of war or conflict. The correlation between Mars' appearance and earthly events was probably coincidental, but it strengthened the belief that celestial movements directly influenced human affairs. The most mysterious wanderer was Mercury, visible only briefly near the horizon just after sunset or before sunrise. Its rapid movement across the sky and its elusive nature made it the messenger of the gods in many mythologies. Those who could predict its appearances were revered as having special connections to the divine realm. As human societies grew more complex, so did their astronomical observations. The development of agriculture required more precise timing than nomadic life, creating a need for more accurate calendars. This drove the development of systematic skywatching, with certain individuals specializing in the observation and interpretation of celestial phenomena. These early astronomers were often also priests, shamans, or other religious leaders, reflecting the deep connection between astronomy and spirituality that would persist for thousands of years. They began to keep records of their observations, first in memory and oral tradition, later in primitive written forms. These records allowed them to identify longer-term patterns and cycles that a single lifetime of observation could not reveal. The concept of the celestial sphere emerged from these early observations. To the naked eye, the stars appeared to be fixed to the inside of a great dome that rotated around the Earth each night. This model, while ultimately incorrect, provided a useful framework for understanding and predicting celestial motions. It also reinforced the sense that Earth was the centre of creation, with the entire universe revolving around human concerns. Within this celestial sphere, observers identified the ecliptic, the path that the sun appeared to follow across the sky over the course of a year. The constellations that lay along this path became known as the zodiac, and they took on special significance in both calendrical and astrological systems. The movement of the sun through these constellations marked the progression of seasons, while the positions of planets within them were believed to influence earthly events. Different cultures developed their own unique interpretations of the star patterns, creating a rich diversity of sky mythologies. The constellation we know as the Big Dipper was seen as a great bear by many cultures, but others saw it as a wagon, a plough, or a group of sages. These different perspectives reflect the universal human tendency to impose familiar patterns on the apparent chaos of the night sky. The development of agriculture also led to the recognition of the precession of the equinoxes, though this phenomenon was not fully understood until much later. Careful observers noticed that the point where the sun rose on the first day of spring slowly shifted over very long periods of time. This discovery hinted at the vast scales of cosmic time that would later revolutionize human understanding of the universe. As civilizations began to build permanent settlements, they often oriented their structures according to astronomical principles. Temples, burial chambers, and other important buildings were aligned with the rising or setting points of significant stars or with the cardinal directions. This practice served both practical and spiritual purposes, connecting human architecture to the cosmic order. The first crude astronomical instruments began to appear during this period. Stone circles, wooden posts, and simple sighting devices allowed for more precise observations of celestial positions and movements. These tools represented humanity's first attempts to extend their natural senses and create more accurate records of sky phenomena. Trade routes between different regions led to the exchange of astronomical knowledge, creating the first international scientific collaborations. Merchants and travellers carried stories of how different peoples interpreted the same celestial events, leading to a gradual synthesis of astronomical traditions. This exchange also revealed that the same stars were visible from different locations, suggesting that the Earth was larger than many had imagined. The development of writing systems revolutionized astronomical record-keeping. What had once been preserved only in memory and oral tradition could now be recorded permanently, allowing for the accumulation of observational data over centuries. These written records would later provide the foundation for more sophisticated astronomical theories and predictions. Yet even with these advances, the fundamental mystery remained. The stars continued to appear as they had for countless generations, showing no obvious signs of change or development. They seemed eternal and unchanging, burning with the same intensity and appearing in the same patterns that had guided the first human skywatchers. What these early observers could not know was that they were looking into the past. The light reaching their eyes had travelled across vast distances of space, carrying information about stellar conditions that had existed years, decades, or even centuries before. The stars they thought they were seeing in the present moment were actually images of the cosmic past, preserved in the light that had finally completed its journey to Earth. This was the beginning of humanity's long journey toward understanding the true nature of the universe. From these humble origins, humans looking up at the night sky and wondering what they saw, would eventually emerge the sophisticated science of astronomy, with its revelation that the stars we see tonight are not as they are, but as they were when their light began its journey across the cosmic dark. As the first cities rose from the fertile deltas of great rivers, something profound shifted in humanity's relationship with the stars. No longer content to simply observe and wonder, these early civilizations began to organize, systematize, and most importantly to record their understanding of the celestial realm. The transition from nomadic stargazing to settled astronomical observation marked the beginning of science as we know it. In the land between the Tigris and Euphrates rivers, the Sumerians built the world's first cities and developed the first known writing system. Their cuneiform script, pressed into clay tablets, captured not only the mundane records of trade and governance, but also the movements of celestial bodies. These tablets, baked hard by the sun and preserved in the dry earth for millennia, represent humanity's first attempts to create a permanent scientific record. The Sumerian priests, who served as the civilization's astronomers, established the first systematic observations of the night sky. They noticed that certain stars appeared to move in relation to others, identifying what we now know as the planets. They gave these wandering stars names that reflected their characteristics: Nergal for the red planet Mars, Nabu for the quick-moving Mercury, and Ishtar for the brilliant Venus that appeared as both morning and evening star. But it was their successors, the Babylonians, who truly revolutionized astronomical observation. Working from the great ziggurat towers that dominated their cities, Babylonian astronomers created the first accurate calendar systems, predicting eclipses and planetary movements with remarkable precision. Their astronomical diaries, meticulously maintained for over 7 centuries, recorded the positions of planets, the phases of the moon, and unusual celestial events. The Babylonians divided the sky into the first zodiac, creating 12 equal segments along the ecliptic, the path of the sun through the stars. Each segment was associated with a constellation and a month of the year, providing a framework that would influence astronomical and astrological thinking for thousands of years to come. They also developed the first mathematical models for predicting planetary motion, using complex arithmetic progressions that could forecast where planets would appear in the sky months or even years in advance. What made the Babylonian achievement so remarkable was not just their observational skill, but their patience. They understood that celestial patterns revealed themselves only over long periods of time. A single observer might notice that Mars appeared brighter during certain seasons, but only generations of careful record-keeping could reveal the planet's complete cycle of movements. This commitment to long-term observation established the foundation of scientific methodology, the systematic accumulation of data over time to reveal underlying patterns and principles. Meanwhile, along the Nile River, Egyptian civilization was developing its own sophisticated understanding of the cosmos. The Egyptians noticed that the annual flooding of the Nile, upon which their entire agricultural system depended, coincided with the first appearance of the star Sirius just before dawn. This correlation led them to develop a calendar based on stellar observations, making them among the first to recognize that the solar year was approximately 365 days long. Egyptian astronomers identified 36 decans, groups of stars that rose just before dawn at 10-day intervals throughout the year. These decans were used to mark the passage of time during the night, providing the Egyptians with the world's first star clock. The walls of tombs and temples were decorated with star maps showing the deacons and their associated deities, reflecting the deep connection between astronomical observation and religious belief. The Great Pyramids of Giza, built around 2500 BCE, represent perhaps the most ambitious astronomical alignment project ever undertaken. The pyramids were oriented with incredible precision to the cardinal directions, and their internal passages were aligned with specific stars. The Great Pyramid's descending passage pointed toward the pole star of that era, while the ascending passage was aligned with the star Thuban in the constellation Draco. These alignments were not merely decorative but reflected the Egyptian belief that the pharaoh's soul would travel along stellar pathways to join the gods in the afterlife. The Egyptians also developed sophisticated methods for timekeeping using the sun's shadow. Their obelisks served as giant sundials, casting shadows that marked the hours of the day. They created water clocks for nighttime use, allowing them to measure time even when the sun was not visible. These innovations in timekeeping were driven by their astronomical observations and their need to schedule religious rituals at specific times. In the Indus Valley, another great civilization was making its own astronomical observations. While the Indus Valley script remains undeciphered, archaeological evidence suggests that these people had a sophisticated understanding of celestial cycles. Their cities were laid out according to cardinal directions, and they developed a standardized system of weights and measures that may have been based on astronomical observations. The later Vedic civilization in India developed a rich astronomical tradition that was deeply integrated with religious and philosophical thought. The Vedic texts contain detailed descriptions of celestial phenomena, including references to eclipses, planetary movements, and the precession of the equinoxes. Indian astronomers developed sophisticated mathematical techniques for calculating planetary positions and created some of the most accurate early calendars. The Vedic understanding of time was cyclical rather than linear, with vast cosmic cycles called kalpas that lasted billions of years. This conception of deep time was unique among ancient civilizations and remarkably close to modern scientific understanding of the age of the universe. Indian astronomers also developed the concept of zero and positional notation, mathematical innovations that would later revolutionize astronomical calculations. In China, a different but equally sophisticated astronomical tradition was emerging. Chinese astronomers were the most systematic observers of celestial phenomena in the ancient world, keeping detailed records of comets, novae, and other unusual events. They divided the sky into 28 lunar mansions, each associated with a different day of the lunar month. Chinese star maps, some dating back over 2,000 years, are among the most accurate produced in the ancient world. The Chinese developed a unique approach to astronomy that emphasized the connection between celestial events and earthly governance. They believed that the emperor ruled by the mandate of heaven, and that unusual celestial phenomena could indicate divine displeasure with the ruler. This belief made astronomy a matter of political importance, leading to the establishment of official astronomical bureaus and the careful monitoring of the sky for signs of cosmic disorder. Chinese astronomers were particularly skilled at observing and recording what they called guest stars, stars that appeared suddenly in the sky and then faded away. These observations, preserved in official court records, provide modern astronomers with valuable data about historical supernovae and other stellar explosions. The Chinese were also the first to observe and record sunspots, challenging the widespread belief that the sun was a perfect, unchanging celestial body. The development of the compass in China led to more precise methods of determining direction and orientation. Chinese astronomers used magnetic compasses to create accurate star maps and to orient their buildings and cities according to astronomical principles. They also developed sophisticated armillary spheres, three-dimensional models of the celestial sphere that could be used to predict the positions of stars and planets. Across the Pacific, the Polynesian peoples were developing their own remarkable astronomical tradition. Without written records or sophisticated instruments, they navigated across thousands of miles of open ocean, using only their knowledge of the stars, waves, and wind patterns. Polynesian navigators memorized the positions of hundreds of stars and learned to read the subtle signs that indicated the presence of distant islands. The Polynesian navigation system, passed down through generations of master navigators, represents one of the most sophisticated practical applications of astronomical knowledge ever developed. navigators learned to identify star compasses, sets of stars that rose and set at specific points on the horizon, and to use these stellar landmarks to maintain their course across the trackless ocean. They also observed the behaviour of seabirds, the patterns of waves, and the colour of the water to supplement their astronomical navigation.
In the Americas, civilizations were developing their own unique astronomical traditions. The Maya, in particular, created one of the most accurate calendar systems ever devised. Their long count calendar could track dates across millions of years, and their calculations of the length of the solar year differed from the true value by only minutes. Maya astronomers made precise observations of Venus, Mars, and the Moon, and they could predict eclipses with remarkable accuracy. Maya cities were often oriented according to astronomical principles, with important buildings aligned to capture the light of rising or setting stars at specific times of the year. The Pyramid of Kukulkan at Chichen Itza, for example, is oriented so that the shadow of the feathered serpent appears to descend the pyramid steps during the spring and autumn equinoxes. These alignments reflected the Maya belief that their building should be in harmony with the cosmic order. Maya developed a sophisticated understanding of cyclical time, with multiple calendars running simultaneously to track different types of temporal cycles. They recognized that astronomical events followed predictable patterns and used this knowledge to schedule religious ceremonies, agricultural activities, and political events. Their Venus tables could predict the planet's movements over centuries, and their eclipse tables warned of times when the sun or moon would be eaten by celestial monsters. What united all these ancient civilizations was their recognition that careful observation of the sky could reveal patterns that were useful for both practical and spiritual purposes. They developed increasingly sophisticated methods for recording and analyzing celestial phenomena, laying the groundwork for the scientific revolution that would eventually transform human understanding of the universe. Yet despite their remarkable achievements, these ancient astronomers shared a common limitation. They could only observe the sky with their naked eyes. The stars appeared as points of light whose distance and true nature remained mysterious. They seemed eternal and unchanging, providing a sense of stability and order in a world of constant flux. What none of these ancient observers could have imagined was that the light reaching their eyes from the stars had been traveling for years, decades, or even centuries before arriving at Earth. The stars they mapped so carefully were not as they appeared in the present moment, but as they had been in the past. The universe they thought they were observing was actually a museum of cosmic history, with each star showing them a different moment in the deep past. This fundamental truth about the nature of light and time would remain hidden for thousands of years, waiting for the development of new instruments and new ways of thinking about the universe. But the careful observations and meticulous records of these ancient civilizations would prove invaluable when that revelation finally came. The star catalogs they created, the eclipse predictions they made, and the calendars they developed would all contribute to humanity's eventual understanding that we see the stars not as they are, but as they were. The stage was set for the next great leap in astronomical understanding. The ancient world had established the importance of systematic observation and mathematical analysis. The foundations of scientific methodology were in place. Now it would fall to the philosophers and mathematicians of ancient Greece to begin asking not just what happened in the sky, but why it happened, questions that would ultimately lead to the modern understanding of light, time, and the vast scales of the universe. Wisdom across the Mediterranean, their scrolls and calculations finding sanctuary in the growing centers of Islamic learning. The torch of celestial knowledge once carried by Greek philosophers and Alexandrian scholars, now passed into hands that would polish it until it gleamed with unprecedented brilliance in the heart of Baghdad, where the Tigris curved like a celestial arc through the desert, stood a building that would reshape humanity's understanding of the cosmos. The Beit al-Hikmah, the House of Wisdom, rose from the earth like a monument to human curiosity, its halls echoing with the whispered calculations of men who dared to measure the immeasurable here. In the early centuries of the Islamic era, scholars from distant lands gathered like pilgrims to a sacred shrine, each carrying fragments of ancient knowledge that would be woven into a tapestry more magnificent than any single culture had ever created. The Caliph al-Mun walked these corridors with the reverence of a man who understood that true power lay not in the sword, but in the mind's ability to unlock the secrets of creation under his patronage. Translators worked by lamplight, rendering the astronomical treasures of Greece, India, and Persia into Arabic script. Ptolemy's Almagest found new life in these careful hands, while Hindu mathematical innovations merged with Greek geometric precision to create tools of unprecedented accuracy. Muhammad ibn Musa al-Khwarizmi bent over his calculations, the numbers flowing like water across parchment. His Zij, astronomical tables more precise than any before them, would guide navigators across endless seas and help farmers calculate the perfect moment for planting. In his work, the abstract beauty of mathematics married the practical needs of a civilization that stretched from Spain to the borders of China. Each calculation was a prayer, each observation a step closer to understanding the divine architecture of the heavens. The scholars of Baghdad understood something their predecessors had glimpsed but never fully grasped, that the universe was not a static tapestry hung in the celestial dome, but a dynamic system of incredible complexity and beauty. They observed with patience that bordered on meditation, recording the subtle dance of planets with an accuracy that would not be surpassed for centuries. Their astrolabes, crafted with the precision of jewelers and the insight of philosophers, became windows through which mortals could peer into the clockwork of eternity across the Islamic world. In observatories perched on rooftops and in gardens where fountains whispered beneath star-drunk skies, astronomers pursued their celestial quarry with the dedication of mystics. Abu Abdullah al-Battani, known to later generations as Albategnius, stood in the ruins of ancient Haran, where star worship had once flourished under earlier civilizations. Here, among the weathered stones that had witnessed millennia of celestial observation, he began measurements that would correct errors in Ptolemy's work and reveal truths about our cosmic neighborhood that had remained hidden for 800 years. Battani's hands moved with surgical precision as he adjusted his instruments, each angle calculated to capture the exact position of the sun at its highest point. Day after day, season after season, he tracked the solar path across the heavens with an obsession that transformed dedication into art. His measurements of the solar year, 365 days, 5 hours, 46 minutes, and 24 seconds came so close to modern calculations that the difference measured only minutes. In an age when most of humanity counted days by the rise and fall of shadows, he had achieved a precision that bordered on the supernatural. But al-Battani's true gift lay in his understanding that the heavens themselves were not changeless, where Ptolemy had seen eternal perfection. The Syrian astronomer detected subtle motion, gradual shifts that spoke of a universe far more dynamic than anyone had dared imagine. His measurements of stellar positions revealed that the stars themselves participated in a vast, almost imperceptible dance, their coordinates shifting over centuries in a phenomenon that would later be understood as the precession of the equinoxes. Working alone in the pre-dawn darkness, al-Battani would align his quadrant with Venus as she appeared as the morning star, her light cutting through the purple twilight like a diamond set in velvet. His calculations of her orbital period achieved an accuracy that would not be improved upon until the age of telescopes. Each observation was a conversation with the cosmos. Each measurement a whispered question posed to the infinite silence that surrounded the small oasis of warmth and life where humanity made its home. The astronomer's workshop became the temple where mathematics served as liturgy and precision as prayer. Al-Battani's students gathered around him like disciples, learning not just the techniques of measurement, but the philosophy of patience that made such accuracy possible. They understood that they were participating in something greater than themselves, adding their voices to a conversation that had begun in the ziggurats of Babylon and would continue long after their bones had returned to dust in the mountains of Afghanistan, where ancient trade routes carved paths through stone and snow. Abu Rayyan al-Biruni pursued knowledge with the hunger of a man who understood that wisdom was the only treasure that could not be stolen by time or tyrants. Born in the shadow of the Hindu Kush, where cultures mingled like streams flowing together into a great river, al-Biruni possessed a mind that recognized no boundaries between disciplines, no walls between the wisdom of different peoples. Al-Biruni's expeditions into India opened doorways between civilizations that had remained closed for centuries. He learned Sanskrit with the dedication of a monk, studying Hindu and Buddhist astronomical texts until he could read them with the fluency of a native scholar in his hands. The sophisticated mathematical astronomy of India merged with the geometric precision of Greek tradition and the observational accuracy of Islamic science. His translations became bridges spanning cultural chasms, allowing ideas to flow like water. Finding its natural level, the Persian scholar understood that the earth was not the center of a small, cozy universe, but a wandering sphere in an abyss of unimaginable vastness. His calculations of the earth's circumference, performed with instruments of his own design and mathematical techniques that merged traditions from 3 continents, achieved a precision that would not be bettered for 500 years, standing on mountaintops with his astrolabe, measuring the angles between stars and horizon with the patience of a craftsman perfecting a masterpiece. Al-Biruni touched the very edges of infinity. His treatise on India became more than a work of astronomy. It was an exercise in cultural translation that revealed how different societies had evolved unique ways of reading the same celestial script. The Hindu concept of cosmic cycles, vast periods of time that made human history seem like the flutter of a butterfly's wing, merged in his mind with Islamic emphasis on divine unity and Greek passion for geometric harmony. Al-Biruni saw that truth wore different faces in different cultures, but its essence remained constant as the wheeling stars in the quiet of his study. Surrounded by manuscripts in a dozen languages and instruments crafted by the finest metalworkers of 3 empires, Al-Biruni worked by candlelight to reconcile the astronomical traditions of humanity into a single coherent vision. His lunar observations, conducted with mathematical rigor that would have impressed Ptolemy and experimental precision that anticipated Galileo, revealed that the moon's surface was not the smooth pearl imagined by poets, but a rugged landscape of mountains and valleys, shadows and lighting the labyrinthine streets of Cairo, where the Nile's gift of fertility had nurtured scholarship for millennia. Ibn al-Haytham, known to the Latin world as Al-Hazan, revolutionized not just astronomy, but the very methods by which human beings could approach truth. His workshop, cluttered with lenses and mirrors, prisms and measuring devices, became the birthplace of experimental science. Here, theory bowed before observation, and ancient authorities yielded to the evidence of carefully controlled experiments. Al-Haytham's studies of light itself opened new windows into the cosmos. He understood that seeing was not simply a matter of the eye receiving images, but a complex dance between light, object, and observer. His camera obscura, a dark room with a single small opening through which the outside world projected itself in perfect, inverted detail, became a metaphor for human knowledge itself. We see the universe not as it truly is, but as shadows and reflections, images that must be interpreted with careful reasoning and mathematical precision. Great scientists' observations of lunar eclipses revealed that the Earth's atmosphere bent and colored light in ways that had never before been understood standing in the darkness as the moon passed through Earth's shadow. Al-Haytham saw not just a celestial event, but a natural experiment that revealed the properties of air itself. The reddish color of the eclipsed moon told him stories about the envelope of gas that surrounded his world, the ocean of air in which all terrestrial life swam like fish unaware of water. His treatise on the structure of the heavens challenged assumptions that had stood unchallenged since Aristotle, using mathematics and observation rather than philosophical argument. Al-Haytham demonstrated that the celestial spheres of ancient astronomy were mathematical conveniences rather than physical realities. The planets moved through space itself, following paths that could be calculated but not contained within crystalline shells. His vision of the cosmos was more austere than his predecessors, emptier of imagined mechanisms but fuller of wonder at the elegant laws that governed celestial motion. In the pre-dawn hours, when Cairo slept and only scholars and merchants stirred in the darkness, Al-Haytham would climb to his rooftop observatory there. Surrounded by instruments of brass and iron, he would track the progress of planets against the backdrop of stars, recording positions with a precision that transformed astronomy from philosophy into science. His measurements of Mars, conducted over years of patient observation, revealed irregularities in planetary motion that would puzzle astronomers for centuries and eventually lead to the overthrow of circular orbits in favor of elliptical paths. In the gardens of Cordoba, where orange blossoms perfumed air that had known both Christian and Muslim prayers, astronomers of Al-Andalus created instruments of such beauty that they seemed crafted by jinn rather than mortal hands. The astrolabe makers of Islamic Spain achieved a fusion of art and science that transformed calculation into poetry. Their brass and silver instruments adorned with calligraphy that reminded users that the study of the heavens was also worship of their creator. Ibrahim ibn Sinan worked in workshops where the sound of hammers on metal mingled with the whispered prayers of craftsmen who understood that their tools would carry human vision to the very boundaries of creation. Each astrolabe was a miniature universe, its intricate network of rotating discs and engraved scales, capable of solving problems that challenged the greatest mathematicians. In the hands of a skilled observer, these instruments could determine the time of night from star positions, calculate the direction of Mecca from any location on Earth, or predict the moment when the crescent moon would first become visible after the new moon. The Toledan Tables, compiled by al-Zarqali in the hills above the Tagus River, represented the culmination of centuries of Islamic astronomical observation. These ephemerides, calculated with mathematical precision that would not be surpassed for 300 years, tracked the wandering paths of planets with accuracy that enabled navigators to cross trackless oceans and farmers to plant their crops at the optimal moment. Al-Zarqali's measurements of the solar apogee the point in Earth's orbit when our world stands farthest from the sun, detected changes so subtle that they revealed the slow evolution of orbital mechanics over historical time in the hills surrounding Toledo, where Christian, Muslim, and Jewish scholars worked side by side in an atmosphere of intellectual collaboration that would later seem miraculous. Observatories rose like flowers in a garden of learning. The trepidation of the equinoxes, first detected by Islamic astronomers, revealed that even the seemingly eternal rhythm of seasons participated in cycles of such vast duration that human civilization was but a brief chapter in their unfolding. These discoveries whispered of deep time, of changes so gradual they could only be detected through the accumulated observations of Centuria Sabir ibn Aflah, working in the amber light of Seville's evening sky, developed new methods for calculating planetary positions that would influence European astronomy for generations. His Isla al-Majisti corrected errors in Ptolemy's work while developing mathematical techniques that reduced the complexity of astronomical calculation. In his hands, trigonometry became a key that unlocked celestial mechanics, transforming the arduous geometric proofs of ancient astronomy into elegant, algebraic solutions that could be mastered by dedicated students rather than requiring the genius of a Ptolemy or Hipparchus across the medieval Islamic world. From the madrasas of Baghdad to the libraries of Cairo, from the observatories of Isfahan to the workshops of Cordoba, a remarkable synthesis was taking place. Scholars who had inherited the astronomical traditions of Greece, India, and Persia were creating something new, a mathematical astronomy of unprecedented precision and scope. Their Zij, or astronomical tables, compiled from decades of patient observation, became the standard references for calculating planetary positions, eclipse times, and calendar dates throughout the Islamic world and beyond. The Great Observatory of Maraghe, constructed in the mountains of Azerbaijan under the patronage of Hulagu Khan, represented the pinnacle of medieval astronomical institution. Here, Nasser al-Din al-Tusi gathered astronomers from across the known world, Muslims and Christians, Persians and Arabs, Chinese and Europeans, creating an international community of scholars, united by their passion for understanding the cosmos. The Maraghe Observatory became a university of the heavens, where theoretical astronomy met practical observation in an atmosphere of intellectual freedom that produced innovations which would eventually transform European understanding of planetary motion. Al-Tusi's mathematical innovations, particularly his development of linear motion from circular components, solved problems that had puzzled astronomers since antiquity. His Tadkira, a masterwork of mathematical astronomy, demonstrated how the apparently irregular motions of planets could be understood as combinations of uniform circular motions. This work, written in the mountains of Persia 6 centuries before Copernicus, contained mathematical techniques that would later appear in the work of the Polish astronomer who revolutionized European understanding of the solar system. The scholars of Maraghe understood that their work was part of a conversation that transcended national and religious boundaries. They corresponded with colleagues across continents, sharing observations and comparing calculations with the dedication of craftsmen perfecting a collective masterpiece. Their Arabic treatises were copied in libraries from Spain to Central Asia, their mathematical innovations spreading through networks of scholarship that connected the Islamic world in a web of intellectual exchange. Ibn al-Shatir, working in the shadow of the Umayyad Mosque in Damascus, developed planetary models that eliminated the equanta, mathematical device that had troubled astronomers for centuries because it violated the principle of uniform circular motion. His geometric solutions to the problem of planetary motion were so elegant and effective that they would later be adopted by European astronomers who created the heliocentric revolution. Yet Ibn al-Shatir worked within the geocentric framework, demonstrating that scientific progress often comes through the gradual refinement of existing theories rather than their sudden overthrow as the medieval period drew toward its close. The great centers of Islamic learning faced challenges that would test their resilience. The Mongol invasions that swept across Asia left libraries in ashes and observatories in ruins, while political fragmentation fractured the unity that had enabled scholars to collaborate across vast distances. Yet the knowledge accumulated through centuries of patient observation and careful calculation proved more durable than the empires that had nurtured it in the libraries of Córdoba and Seville. Christian scholars working under Muslim rule began translating Arabic astronomical texts into Latin, creating bridges between Islamic science and the emerging universities of medieval Europe. These translations, often collaborative efforts involving Muslim, Christian, and Jewish scholars, preserved not just the conclusions of Islamic astronomy, but its methods and mathematical techniques. The astrolabe, that perfect marriage of art and science, traveled from the workshops of Muslim craftsmen into European monasteries and universities, carrying with it centuries of accumulated knowledge about the measurement of time and the mapping of the heavens. Gerard of Cremona, working in the multicultural environment of 12th century Toledo, translated al-Battani's Zij into Latin, making the Syrian astronomers' precise measurements available to European scholars who had lost much of the mathematical sophistication of ancient astronomy. The Toledan tables of al-Zarqali became the standard reference for European astronomers, their accuracy enabling the calculation of Easter dates and the compilation of new calendars that would regulate the rhythm of medieval Christian life. The manuscript tradition that preserved Islamic astronomical knowledge resembled the very stars. These scholars studied individual points of light scattered across time and space, yet forming patterns that revealed underlying order and beauty. In libraries from Istanbul to Timbuktu, from Samarkand to Granada, copyists worked by lamplight to preserve the calculations and observations that represented humanity's accumulated understanding of the cosmos. Each manuscript was a seed carrying the genetic code of mathematical astronomy, capable of germinating in new soil when conditions permitted. As European scholars began to establish new centers of learning in Paris and Oxford, Bologna and Padua, they built upon foundations laid by their Islamic predecessors, the quadrivium arithmetic, geometry, astronomy, and music that formed the mathematical core of medieval European education. Was populated with techniques and insights that had been developed in the House of Wisdom and refined in observatories from Samarkand to Seville. The very vocabulary of European astronomy bore witness to its Islamic heritage, with words like algebra, algorithm, zenith, and nadir carrying Arabic origins into Latin scientific discourse. Yet perhaps the most important legacy of Islamic astronomy was not any particular discovery or technique, but rather an approach to knowledge that combined reverence for ancient wisdom with willingness to test and refine that wisdom through observation and calculation. The Islamic astronomers had demonstrated that human reason, guided by careful observation and mathematical precision, could penetrate the mysteries of creation and reveal the elegant laws that govern celestial motion. This methodological revolution, as much as any specific discovery, would provide the foundation for the scientific transformations that lay ahead. The stars that had guided Bedouin caravans across Trackless deserts had become laboratories for understanding the fundamental principles that govern the cosmos. And in that transformation lay the seeds of all subsequent astronomical revolution, and so the precious manuscripts journeyed westward, carrying within their carefully copied pages the accumulated wisdom of centuries, ready to kindle new fires of understanding in minds that had long gazed upward in wonder, but lacked the tools to truly seeing the cathedral schools and newly founded universities of medieval Europe. A quiet revolution was beginning to stir. The works of Ptolemy, translated from Arabic into Latin, found their way into the hands of scholars who had been starved of such knowledge for centuries. Thomas Aquinas, the great synthesizer of Christian theology and Aristotelian philosophy, grappled with these astronomical texts, seeking to reconcile the movement of the spheres with divine providence. His careful scholarship helped legitimize the study of the heavens within the framework of Christian learning, preparing the ground for what was to come. The mechanical clocks that began to appear in European cities during the 13th century represented more than mere timekeeping devices. They embodied a new relationship with the cosmos. These intricate mechanisms, with their precise gears and regulated movements, suggested that the universe itself might operate according to discoverable laws rather than the whims of celestial beings. The clockwork metaphor would later prove prophetic, but for now, it simply offered a tantalizing glimpse of mathematical order underlying apparent chaos in the monasteries and courts where learning flourished. Scholars began to notice discrepancies between Ptolemaic predictions and actual observations. The calendar itself had become unreliable, with the spring equinox occurring earlier each year than the calculation suggested. It should religious festivals, so carefully tied to celestial events, were slowly drifting away from their intended seasons. This practical problem would eventually demand a solution that would shake the very foundations of cosmic understanding. The printing press, invented by Johannes Gutenberg in the mid-15th century, transformed how astronomical knowledge spread throughout Europe. No longer did scholars need to rely on hand-copied manuscripts, with their inevitable errors and variations. Now the same text could be reproduced hundreds of times with perfect accuracy, allowing for the widespread dissemination of astronomical tables, treatises, and observations. This technological revolution created the conditions necessary for the next great leap in human understanding of the cosmos. In the cold cathedral tower of Frombork, overlooking the Baltic Sea, a Polish canon named Nicolaus Copernicus spent his nights watching the stars and his days wrestling with mathematical calculations that would not align. Born in 1473 to a merchant family in Turu, Copernicus had studied law and medicine in Italy, where he encountered the full flowering of Renaissance humanism and the rediscovered works of ancient astronomers. But it was in his quiet tower room, surrounded by books and instruments, that he began to perceive a fundamental error in humanity's understanding of its place in the universe. The problem that tormented Copernicus was elegance, or rather, the lack of it in the Ptolemaic system. To account for the observed motions of the planets, astronomers had been forced to add layer upon layer of complexity, epicycles upon epicycles, equants and eccentrics, until the celestial machinery resembled a vast clockwork gone mad. Mercury alone required over 30 separate circles to explain its wandering path across the sky. This offended Copernicus's mathematical sensibilities, trained as they were in the classical ideal that nature's patterns should reveal underlying simplicity and harmony during the long northern winters. As snow covered the cathedral grounds and ice formed along the Baltic shores, Copernicus began to imagine a different arrangement of the cosmos. What if, he wondered, the apparent complexity of planetary motion arose not from the planets themselves, but from the fact that Earth was not the stable center around which everything revolved. What if the Earth itself was in motion, spinning on its axis and orbiting the Sun along with the other planets? The idea was not entirely new. The ancient Greek philosopher Aristarchus of Samos had proposed a heliocentric system 18 centuries earlier, and medieval Islamic astronomers had occasionally considered the possibility, but Copernicus was the first to work out the mathematical details with sufficient precision to demonstrate that such a system could actually account for observed planetary motions more simply and elegantly than the Earth-centered model that had dominated astronomy for over a millennium. Night after night, Copernicus tracked the positions of planets against the background stars, measuring angles with his crude instruments and recording his observations in neat columns of numbers. Gradually, the new pattern began to emerge from his calculations. If the Earth moved around the Sun in a year, then the apparent motion of Mars, Jupiter, and Saturn against the stellar background could be explained as a natural consequence of Earth's changing perspective, like watching distant objects from a moving carriage. The heliocentric model revealed beautiful relationships that had been hidden by the geocentric assumption. The order of the planets naturally fell out from their periods of revolution. Mercury, closest to the Sun, completed its orbit fastest. Venus took longer. Earth's year provided the unit of measurement. Mars, Jupiter, and Saturn followed in majestic procession, their periods increasing with their distance from the central fire. The apparently random looping motions of the outer planets, the retrograde movements that had so puzzled ancient astronomers, suddenly made perfect sense as the result of Earth overtaking these more distant worlds in its faster inner orbit. But Copernicus was no radical revolutionary seeking to overturn established order. He was a church official, deeply embedded in the medieval worldview, and he understood the profound implications of what he was proposing. If the Earth moved, then humanity was no longer at the center of creation. The entire hierarchy of being, with Earth at the bottom, and the celestial spheres ascending toward divine perfection, would collapse. Moreover, if the Earth spun on its axis, as his model required, why didn't objects fly off into space? Why didn't falling stones drift westward as the ground rotated eastward beneath them? For decades, Copernicus refined his calculations in private, sharing his ideas only with a few trusted friends and colleagues. He knew that publication would bring controversy, perhaps even persecution. The Catholic Church, while not yet officially opposed to the heliocentric idea, was increasingly concerned with maintaining doctrinal orthodoxy in the face of the Protestant Reformation. Any theory that seemed to contradict Scripture, and there were biblical passages that clearly spoke of the Sun moving around the Earth, would likely face severe criticism. It was only in 1542, as Copernicus lay dying in his cathedral residence, that he finally agreed to the publication of his great work, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. Legend holds that the first printed copy was placed in his hands on the very day he died, May 24, 1543. Whether or not this story is true, it captures something essential about the man who had spent a lifetime in quiet contemplation of the cosmos. Reluctant to disturb the established order, yet unable to suppress the mathematical truth he had discovered. The publication of De Revolutionibus did not immediately transform astronomy, as one might expect of such a revolutionary work. Indeed, for several decades, the book was largely ignored or dismissed as an interesting mathematical exercise with little bearing on physical reality. The preface added without Copernicus's knowledge by the Lutheran minister Andreas Osiander, suggested that the heliocentric model should be understood as merely a computational convenience rather than a description of how the cosmos actually worked. This diplomatic fiction allowed the book to circulate without immediate condemnation, but it also deflected attention from the radical implications of what Copernicus had proposed. Professional astronomers appreciated the mathematical elegance of the Copernican system, but few were willing to embrace its physical reality. The model still relied on circular orbits and required its own set of epicycles to match observations precisely. So it was not dramatically simpler than the Ptolemaic system it sought to replace. More fundamentally, there was no observable evidence that the Earth was actually in motion. If the Earth orbited the Sun, then the positions of stars should shift slightly throughout the year as our planet changed its viewpoint, a phenomenon called stellar parallax. But no such shifts could be detected with the instruments available in the 16th century. The implications of taking Copernican theory seriously extended far beyond astronomy. If the Earth was just another planet, then the heavens were no longer perfect and unchanging. As Aristotelian philosophy maintained, the distinction between terrestrial and celestial realms fundamental to medieval cosmology would become meaningless. The universe would be vastly larger than previously imagined, since the stars would need to be incredibly distant to explain why their parallax motion remained undetectable. Most disturbing of all, humanity would lose its central position in creation, becoming mere inhabitants of a wandering world in an infinite expanse of space. Yet, gradually, quietly, the Copernican worldview began to take root in the minds of those who studied the heavens most closely. In the universities of Protestant Germany and Denmark, where intellectual freedom was somewhat greater than in Catholic territories, a new generation of astronomers emerged who took the heliocentric hypothesis seriously. They began to search for additional evidence that might confirm or refute the radical proposition that the Earth moved through space on a small island in the Risund Strait between Denmark and Sweden. A most unusual observatory took shape in the closing decades of the 16th century. Uraniborg, the castle of Urania, muse of astronomy, was the brainchild of Tycho Brahe, a Danish nobleman whose approach to understanding the cosmos would be as unconventional as his appearance, having lost part of his nose in a duel during his student days. Tycho wore a prosthetic made of gold and silver that glinted in the lamplight. As he bent over his instruments night after night, making observations of unprecedented precision, Tycho had been inspired to devote his life to astronomy. By witnessing a conjunction of Jupiter and Saturn in 1563, the event occurred at a noticeably different time than the astronomical tables predicted, revealing to the young nobleman that even the best available data about celestial motions was seriously flawed. If astronomy was to progress, he realized it would need a foundation of far more accurate observations than any previous generation had attempted to gather. With the patronage of King Frederick II of Denmark, Tycho transformed the island of Vane into a center of astronomical research. Unlike anything the world had ever seen, Uraniborg was both castle and laboratory, containing workshops for crafting precision instruments, a printing press for publishing results, and living quarters for a community of assistants, students, and visiting scholars. The building itself was designed according to cosmic principles, with its architecture reflecting the harmony of the spheres that Tycho sought to measure with ever greater precision. The instruments housed within Uraniborg and its subsidiary observatory, St. Jerneborg, represented the culmination of pre-telescopic astronomy. Tycho's great mural quadrant, mounted permanently on a north-south wall, could measure stellar positions to within 1 or 2 arcminutes, roughly 20 times more accurately than previous astronomers had achieved. His celestial globe, nearly 5 feet in diameter, served as a 3-dimensional star catalog on which the positions of over 1,000 stars were marked with unprecedented precision. But Tycho's greatest contribution to astronomy came not from any single instrument, but from his systematic approach to observation, night after night. For over 20 years, he and his assistants tracked the positions of planets against the stellar background, accumulating a vast database of positional measurements. This was not the occasional observation of previous centuries, but sustained, methodical monitoring of celestial objects over multiple cycles of their motion. The quality and quantity of Tycho's observations would provide future astronomers with the raw material needed to unlock the true laws governing planetary motion. Yet, Tycho himself never fully embraced the Copernican revolution. Though he recognized that the heliocentric model had mathematical advantages over the traditional Earth-centered system, he could not accept that the Earth was actually in motion. His own careful observations had failed to detect stellar parallax, and he remained convinced that if the Earth truly orbited the Sun, such motion should be observable. Instead, Tycho proposed a compromise system in which the Sun and Moon orbited the Earth, while the other planets orbited the Sun. This Tychonic system preserved the Earth's stationary position, while accounting for some of the mathematical elegance of the Copernican model. In 1597, political changes in Denmark forced Tycho to abandon his island observatory and seek new patronage. The Holy Roman Emperor Rudolf II, himself fascinated by astronomy and alchemy, welcomed the great observer to Prague and provided him with a new position as imperial mathematician. There, in the last years of his life, Tycho would encounter a young German mathematician whose theoretical insights would transform the great Dane's meticulous observations into a new understanding of cosmic mechanics. Johannes Kepler arrived in Prague in 1600 as a young man driven by an almost mystical belief in the mathematical harmony underlying the cosmos. Born into a troubled family in the German Duchy of Württemberg, Kepler had survived a difficult childhood, marked by poverty, family dysfunction, and religious persecution, to become one of the most brilliant mathematicians of his generation. His early work on the nested geometric solids that might explain the spacing of planetary orbits had attracted Tycho's attention, leading to an invitation to join the great observer's research team. The collaboration between the two men was not an easy one. Tycho, aristocratic and possessive of his hard-won data, was reluctant to share his most precise observations with the newcomer Kepler, impatient and driven by theoretical insights that Tycho could not always follow. Chafed at being assigned to work on the orbit of Mars, the most difficult of all the planets to track because of its highly elliptical path, yet this apparent mismatch would prove fortuitous, for Mars's stubborn refusal to conform to circular motion would eventually force Kepler to abandon the most fundamental assumption of ancient astronomy. Tycho died suddenly in 1601, possibly from a burst bladder sustained during a formal dinner where etiquette prevented him from leaving the table. Kepler inherited both the position of imperial mathematician and access to the complete archive of Tychonic observations. Now, he could pursue his theoretical investigations without restriction, using the most accurate planetary positions ever recorded to test his ideas about cosmic harmony. Kepler's first major breakthrough came through his analysis of Mars's orbit. Using Tycho's observations, he calculated where the planet should appear At various times according to both the Ptolemaic and Copernican systems, neither model matched the data within the precision of Tycho's measurements. The discrepancies were small, only about 8 arc minutes, but they were consistent and undeniable. A lesser astronomer might have dismissed such tiny errors as observational uncertainty. But Kepler had too much faith in Tycho's precision to doubt the measurements. If the theories didn't match the data, then the theories had to be wrong for nearly 6 years. Kepler struggled to find a geometric curve that would match Mars's observed positions. He tried every variation of circles and epicycles he could imagine, adjusting parameters and adding complexity until his calculations filled hundreds of pages. With meticulous arithmetic, the work was exhausting and often frustrating. Kepler later wrote that his calculations on Mars could fill 70 volumes. But gradually a pattern began to emerge that would revolutionize humanity's understanding of celestial mechanics. The breakthrough came when Kepler abandoned the ancient assumption that planetary orbits must be circular. What if, he wondered, Mars moved in an ellipse with the Sun at one focus? The mathematics of elliptical motion was more complex than circular motion, but when Kepler worked through the calculations, he found that an elliptical orbit matched Tycho's observations perfectly. The discrepancies that had tormented him for years vanished as if by magic, but Kepler was not content with solving the problem of Mars alone. If one planet moved in an ellipse, perhaps they all did. Over the following years, he extended his analysis to the other planets, discovering that each moved in its own elliptical orbit with the Sun at one common focus. This became his first law of planetary motion. The orbit of every planet is an ellipse with the Sun at one of the two foci. The second law emerged from Kepler's attempt to understand how planetary speed varied along these elliptical paths. Ancient astronomy had assumed that celestial objects moved at constant speeds. But Kepler's analysis of Tycho's data revealed that planets moved faster when closer to the Sun and slower when farther away. The relationship was precise and mathematical. A line drawn from the Sun to a planet sweeps out equal areas in equal times. This meant that a planet's orbital speed was inversely related to its distance from the Sun at any given moment. The third law, published in 1619 in Kepler's work Harmonices Mundi, The Harmony of the World, revealed an even deeper pattern in planetary motion. The square of a planet's orbital period was proportional to the cube of its average distance from the Sun. This mathematical relationship connected the sizes of planetary orbits to their periods of revolution, revealing a fundamental harmony in the cosmic architecture that Kepler saw as evidence of divine mathematical design. Kepler's laws represented the first accurate description of planetary motion in the history of astronomy. They were purely empirical, derived from observations rather than theoretical assumptions, and they worked with stunning precision. Yet Kepler himself never fully understood why planets moved according to these laws. He imagined various mechanical explanations involving magnetic forces emanating from the Sun, but lacked the mathematical tools to develop a complete theory of celestial mechanics that would require the genius of a man not yet born. When Kepler published his discoveries, the year 1609 brought news to Italy of a curious Dutch invention, a combination of lenses that could make distant objects appear closer and larger. The device, initially marketed as a military tool for observing enemy ships at sea, consisted of a concave eyepiece and a convex objective lens mounted in a tube. When Galileo Galilei, professor of mathematics at the University of Padua, heard reports of this spyglass, he immediately grasped its potential significance and set about constructing an improved version of his own Galileo was already well known in intellectual circles for his work on motion and mechanics. But it was his decision to turn the newly invented telescope toward the heavens that would make him immortal on a clear evening in late 1609. He pointed his handmade instrument at the moon and saw something that no human being had ever witnessed. The lunar surface was not smooth and perfect, as Aristotelian philosophy maintained, but rough and mountainous, scarred by craters and marked by shadows that shifted with the changing angle of sunlight. This first telescopic observation shattered a fundamental assumption of ancient cosmology. If the moon, the nearest celestial body, was imperfect and Earth-like, then the distinction between terrestrial and heavenly realms began to blur. The celestial sphere was not made of some perfect, unchanging substance. It consisted of worlds that might be similar to our own. Galileo carefully sketched what he saw, producing detailed drawings of lunar phases that revealed the three-dimensional character of Earth's satellite for the first time in human history. But the moon was only the beginning. As winter turned to spring in 1610, Galileo made discovery after discovery that would fundamentally alter humanity's understanding of the cosmos. When he observed Jupiter through his telescope, he noticed what appeared to be 4 small stars nearby. Night after night, he tracked their positions, gradually realizing that these were not distant stars at all, but moons orbiting the giant planet. Here was a miniature solar system, visible through the telescope, demonstrating that not everything in the universe circled the Earth. Discovery of Jupiter's moons, which Galileo diplomatically named the Medicean stars in honor of his potential patron, Cosimo de' Medici, provided powerful support for the Copernican system. If Jupiter could have moons orbiting around it while the planet itself moved through space, then it was entirely reasonable to suppose that Earth could orbit the sun while retaining its own moon. The ancient objection that the moon would be left behind if Earth moved was definitively refuted by this direct observation of celestial mechanics. In action, perhaps even more dramatic, was Galileo's observation of Venus through the telescope. Over the course of several months, he watched the planet go through a complete cycle of phases, just like the moon, but the pattern of phases he observed could only be explained if Venus orbited the sun rather than the Earth. In the traditional geocentric system, Venus should always appear as a crescent when viewed from Earth. Instead, Galileo saw the planet exhibit the full range of phases from new to full, exactly as the Copernican model predicted. When Galileo turned his telescope toward the Milky Way, that faint band of light that had puzzled observers since antiquity resolved into countless individual stars. The universe suddenly became vastly more populous than anyone had imagined, where the naked eye saw only a few thousand stars. The telescope revealed multitudes beyond counting. Each region of sky that appeared empty to unaided vision proved to contain dozens or hundreds of stars. When viewed through the telescope, the cosmos was clearly far larger and more complex than traditional astronomy had supposed. Galileo's telescopic discoveries, published in 1610 in a work called Sidereus Nuncius, The Starry Messenger, created a sensation throughout Europe. The book, written in accessible Latin and illustrated with Galileo's own careful drawings, brought the new astronomy to a wide audience. Suddenly, anyone with access to a telescope could verify these discoveries for themselves. The evidence for the Copernican system was no longer purely mathematical. It had become observational and visual. But not everyone welcomed these revelations. The Catholic Church, already struggling to maintain doctrinal unity in the face of the Protestant Reformation, viewed Galileo's discoveries with growing alarm. In 1616, the Congregation of the Index, placed Copernicus's De Revolutionibus on the list of prohibited books, and Cardinal Bellarmine warned Galileo not to defend the heliocentric theory as physical truth. For several years, Galileo remained relatively quiet, focusing on less controversial aspects of his research. The election of Cardinal Maffeo Barani as Pope Urban VIII in 1623 seemed to offer new hope for the acceptance of Copernican astronomy within the Catholic Church. Barberini had been friendly toward Galileo and was known for his interest in intellectual matters encouraged by this development. Galileo began work on a comprehensive defense of the heliocentric system, structuring it as a dialogue between proponents of different cosmological models. Dialogo sopra I due massimi sistemi del mondo, Dialogue Concerning the Two Chief World Systems, was published in Florence in 1632. After receiving official approval from church censors, the work presented arguments for both the Ptolemaic and Copernican systems through conversations between three characters: Salviati, who argued for the heliocentric model; Simplicio, who defended the traditional Earth-centered view; and Sagredo, an intelligent layman who weighed the evidence presented by both sides, although Galileo had structured the dialogue to appear neutral. Readers could hardly miss which side had the stronger arguments. Salviati demolished the traditional objections to Earth's motion one by one, while Simplicio often appeared foolish and out of his depth. The work was written in Italian rather than Latin, making it accessible to educated readers throughout Italy rather than limiting it to professional scholars. Within months, the book had created a stir throughout Catholic Europe. Pope Urban VIII, however, was not pleased with the work he had indirectly encouraged. The character of Simplicio, who voiced some of the Pope's own objections to the Copernican system, seemed to make the pontiff appear ridiculous. Moreover, the political situation in Europe had deteriorated. With Catholic forces suffering defeats in the 30 Years' War, the Pope, under pressure from conservative cardinals and Jesuit astronomers, felt that he could not afford to appear weak on matters of doctrine. In 1633, Galileo was summoned to Rome to face trial before the Roman Inquisition. The charges against him were serious. He had violated the 1616 injunction not to teach or defend the Copernican system, and his dialogue was seen as a work of advocacy rather than neutral scholarly inquiry. Despite his age, he was nearly 70 and poor health. Galileo was subjected to intense interrogation by church officials determined to make an example of the famous astronomer. The trial of Galileo was not simply a conflict between science and religion, as it is often portrayed, but a complex political and intellectual crisis involving questions of authority, interpretation, and the limits of human knowledge. Many prominent Jesuits were themselves skilled astronomers who understood the strengths of the Copernican system, but they were reluctant to challenge church doctrine openly. The issue was not whether mathematical astronomy could be useful for practical purposes, but whether human reason could determine the true structure of the cosmos independently of revealed truth. Faced with the threat of torture and execution, Galileo chose to recant his support for the heliocentric system on June 22, 1633. Kneeling before the assembled cardinals of the Inquisition, he formally abjured the false doctrine that the sun was the center of the world and that the earth moved around it. Legend holds that as he rose from his knees, he muttered under his breath, "Eppur si muove," and yet it moves. But there is no historical evidence for this dramatic gesture. The real Galileo was too practical a man to risk his life for the sake of a defiant gesture. Galileo spent the remaining Years of his life under house arrest at his villa outside Florence, forbidden to publish or teach about astronomy, yet even in confinement, his mind remained active. He continued to make observations, corresponded with scholars throughout Europe, and worked on a new book about mechanics and motion that would prove to be one of his most important scientific contributions. The trial had silenced him publicly, but it could not stop the spread of the ideas he had championed while Galileo languished. Under house arrest, the intellectual centers of Northern Europe were nurturing a new generation of natural philosophers who would carry forward the mathematical study of the cosmos in Protestant lands, where the authority of the Roman Inquisition held no sway. Scholars could pursue the implications of Copernican astronomy with greater freedom, building upon the foundations laid by Kepler's laws and Galileo's telescopic discoveries. René Descartes, the French philosopher and mathematician, proposed a mechanical model of the cosmos in which planets were carried around the sun by vast whirlpools of subtle matter, while his specific theory proved incorrect. Descartes' approach was profoundly influential in suggesting that celestial motions could be explained through the same mechanical principles that govern terrestrial phenomena. The heavens were no longer a realm apart from earthly physics, but subject to the same mathematical laws that describe the motion of falling stones and flowing water in England. A group of natural philosophers associated with Gresham College, and later the Royal Society, began to develop experimental approaches to understanding both terrestrial and celestial mechanics. Robert Hooke investigated the properties of springs and pendulums, discovering mathematical relationships that seemed to govern elastic motion. Christopher Wren applied geometric principles to architectural problems, while also contributing to astronomical theory. These men shared a conviction that the natural world operated according to discoverable mathematical laws, and that human reason could uncover these laws through careful observation and mathematical analysis. The stage was being set for a grand synthesis that would unite terrestrial and celestial mechanics under a single mathematical framework, but this achievement would require a mind of extraordinary mathematical power, combined with the physical insights needed to understand the fundamental forces governing motion throughout the universe. Such a mind was developing in the quiet countryside of Lincolnshire, where a young man named Isaac Newton was beginning to contemplate the deepest mysteries of natural philosophy. As the 17th century progressed, the cumulative weight of evidence in favor of the heliocentric system became increasingly difficult to ignore. Astronomers throughout Europe were making observations that could only be explained by assuming that the Earth orbited the Sun, the phases of Venus, the moons of Jupiter, the mountains of the Moon, the countless stars revealed by the telescope. All of these discoveries pointed toward a cosmos far grander and more complex than the medieval imagination had conceived. Fundamental questions remained unanswered. If the planets orbited the king und the sun according to Kepler's mathematical laws, what force held them in their elliptical paths? Why did objects fall toward the Earth if our planet was hurtling through space at tremendous speed? How could the same mathematical principles that described the arc of a cannonball also govern the motion of Mars in its orbit around the Sun? The answers to these questions would require a new kind of mathematics and a deeper understanding of the nature of force and motion than any previous generation had achieved. The astronomical revolution that had begun with Copernicus's quiet calculations in his cathedral tower was nearing its climax. The mathematical tools were in place. The observational evidence was compelling, and brilliant minds throughout Europe were grappling with the fundamental questions of cosmic mechanics. What was needed now was a synthesis that would bring together all of these separate insights into a single, comprehensive theory of universal motion, a theory that would not only explain the movements of the planets, but also reveal the mathematical harmony underlying all of nature in the orchards and gardens of England. As the plague years of the 1660s forced universities to close and scholars to retreat to the countryside, that synthesis was beginning to take shape in the mind of a young Cambridge graduate who would soon revolutionize humanity's understanding of the cosmos more profoundly than any thinker since. Aristotle, the age of mathematical astronomy, was about to give way to the age of mathematical physics, and with it, the ancient dream of understanding the music of the spheres would finally be realized in the language of equations and universal laws. The great clockwork of heaven had revealed its first secrets, yet the deeper mysteries remained, locked behind veils of distance and time. As the 17th century drew to its close, the scattered observations of centuries past began to coalesce into something grander, a unified understanding that would transform not merely how humanity saw the stars, but how it comprehended the very fabric of existence itself. In the quiet chambers of Trinity College, Cambridge, a young mind wrestled with questions that had haunted philosophers since the dawn of thought. Isaac Newton, born in the year Galileo died, inherited a universe already transformed by the telescope's revelations, yet still fragmented by incomplete understanding. The planets moved in their elliptical paths, as Kepler had described. But why? What invisible force guided their eternal dance through the cosmic void? The answer came not in a moment of sudden revelation, but through years of painstaking mathematical exploration that would forever change humanity's relationship with the stars. Newton's law of universal gravitation revealed that the same force pulling an apple toward Earth's surface also held the moon in its orbit, guided the planets around the sun, and governed the motion of distant stars in their celestial sphere. For the first time in human history, the heavens and earth were united under a single mathematical law. The stars, once seen as divine lights, fixed in crystal spheres, now revealed themselves as distant suns, burning with the same fires that warmed Earth's surface. Bound by the same gravitational threads that kept humanity anchored to its terrestrial home, the universe became not a collection of separate realms, terrestrial and celestial, but one vast, interconnected system governed by comprehensible laws. Newton's Principia Mathematica, published in 1687, marked the moment when astronomy transformed from ancient stargazing into modern astrophysics. The book's dense mathematical proofs and geometric diagrams seemed dry compared to the poetic cosmologies of earlier ages. Yet within its pages lay revelations more profound than any myth. The stars, Newton showed, were not merely lights in the sky, but massive bodies exerting gravitational influence across the vast emptiness of space. As word of Newton's discoveries spread through the coffee houses and academies of Europe, astronomers began to see the night sky with new eyes. Every star became a question. How far away? How massive? What held it in place? The comfortable certainties of the geocentric universe had already crumbled under Copernican and Galilean assault. But now even the heliocentric model revealed itself as merely one small part of an infinitely larger cosmos. The implications struck some observers with almost religious awe. If the same laws govern celestial and terrestrial motion, then the universe possessed a fundamental unity that transcended the apparent chaos of earthly experience. The stars, dancing in their courses according to mathematical principles, suggested a cosmic order more beautiful and perfect than any human creation. Yet this same revelation carried a darker undertone. If humanity was not the center of creation, if Earth was merely one planet among many orbiting one star among countless others, what did this mean for human significance in the grand scheme of existence? Newton himself seemed to sense the profound implications of his work. In later years, he would write that he felt like a child playing on the seashore, occasionally finding a smoother pebble or prettier shell while the great ocean of truth lay undiscovered before him. The metaphor captured perfectly the moment in which astronomy found itself, having glimpsed the mathematical unity underlying all natural phenomena. Yet aware that this glimpse revealed the magnitude of what remained unknown with Newton's gravitational framework established, astronomers of the 18th century embarked upon the systematic measurement of the cosmos. The stars, no longer mere points of light, demanded precise observation and mathematical analysis. Every telescope turned skyward became an instrument for probing the fundamental structure of reality itself. Challenge was immense. Even the nearest stars showed no perceptible movement as Earth orbited the Sun, suggesting distances so vast they defied easy comprehension. Attempts to measure stellar parallax, the tiny apparent shift in a star's position as Earth moved from one side of its orbit to the other, failed repeatedly, pushing the boundaries of instrumental precision beyond what 18th century technology could achieve. Yet these failures themselves carried profound meaning. Each unsuccessful attempt to detect stellar parallax pushed the stars further into the cosmic distance, revealing a universe far larger than anyone had imagined. If the nearest stars showed no measurable parallax, they must lie at distances thousands of times greater than the diameter of Earth's orbit around the Sun. The implications staggered even the most adventurous minds of the age. In 1718, Edmund Halley made a discovery that would revolutionize understanding of stellar nature, comparing ancient star positions recorded by Hipparchus and Ptolemy with contemporary observations. Halley detected something unprecedented. Certain bright stars had moved. Sirius, Arcturus, and Aldebaran had shifted their positions relative to neighboring stars over the intervening centuries. Discovery of stellar proper motion shattered the last vestiges of the ancient conception of fixed stars. These celestial lights, seemingly eternal and unchanging, were revealed as dynamic bodies moving through space at tremendous velocities. The stars were not painted on a celestial sphere, but scattered throughout three-dimensional space at varying distances, each following its own trajectory through the cosmic void. This revelation transformed astronomical observation from static cataloging to dynamic study. Every star became a moving target, its apparent position changing slowly but measurably over time. Astronomers began to conceive of the stellar realm not as a fixed backdrop for planetary motion, but as a vast, evolving system of bodies in constant motion. The mathematics of stellar motion required new conceptual frameworks. If stars moved through space, what forces governed their motion? Were they bound to some larger structure, or did they wander freely through the void? The questions multiplied faster than answers, yet each question revealed new depths of cosmic complexity. Some astronomers began to speculate about stellar systems, groups of stars bound together by gravitational attraction, perhaps orbiting around common centers of mass in patterns too vast and slow to be perceived within human lifetimes. The possibility that stars might cluster into organized structures, analogous to planetary systems but on scales millions of times larger, opened new vistas for astronomical imagination. In the market town of Bath, England, a German immigrant named William Herschel pursued two seemingly unrelated passions with equal devotion. By day, He composed music and conducted concerts for this fashionable society. By night, he ground telescope mirrors and explored the depths of space with an intensity that bordered on obsession. Herschel's amateur status in astronomy proved to be an advantage rather than a limitation. Unencumbered by institutional traditions or theoretical preconceptions, he approached the night sky with fresh eyes and unprecedented systematic thoroughness. Where previous astronomers had focused on individual objects or specific phenomena, Herschel undertook nothing less than a comprehensive survey of the heavens. His discovery of Uranus in 1781 brought him sudden fame and royal patronage, but this achievement marked only the beginning of his revolutionary contributions to astronomy. Herschel understood that the key to unlocking cosmic secrets lay not in occasional observations but in systematic, comprehensive surveys that would reveal the large-scale structure of the stellar universe. Working alongside his devoted sister Caroline herself, a pioneering astronomer who would discover 8 comets and become the first woman to receive scientific recognition from the Royal Astronomical Society, William Herschel embarked upon the most ambitious observational program in astronomical history. Night after night, year after year, they methodically swept the sky, cataloging every object visible through their increasingly powerful telescopes. Herschel's surveys revealed phenomena that challenged every existing model of cosmic structure. Nebulae, faint, cloudy patches of light scattered across the sky, appeared in such numbers and variety that they clearly represented a major component of the universe, previously almost entirely overlooked. Some nebulae showed distinct structure, with spiral arms or central condensations. Others appeared as smooth, oval patches of light. Still others contained bright stars embedded in diffuse luminosity. William Herschel's attempts to understand these mysterious objects led him to propose what he called island universes, vast systems of stars so distant that they appeared as faint nebular patches to terrestrial observers. The idea was breathtaking in its implications. If nebulae were indeed distant stellar systems comparable to the Milky Way, then the universe contained not thousands or millions of stars, but countless billions scattered across space in organized structures of unimaginable scale. Yet Herschel's island universe hypothesis faced serious observational challenges. Some nebulae could be resolved into individual stars with powerful telescopes, supporting the distant stellar system interpretation. Others remained resolutely cloudy, even under the highest magnifications, suggesting they might be genuinely nebulous rather than stellar in nature. The question of nebular composition would haunt astronomy for more than a century. Caroline Herschel's own contributions extended far beyond her role as William's assistant. Her systematic comet hunting resulted in discoveries that established her as a formidable astronomer in her own right. More significantly, her meticulous record-keeping and data analysis provided the foundation for much of William's theoretical work. The Herschel surveys represented a true collaboration between 2 brilliant minds, each bringing unique skills to their shared exploration of cosmic mysteries. Herschel's work revealed that the universe possessed structure on multiple scales. Individual stars clustered into double and multiple systems, stars grouped into larger aggregations within the Milky Way. The Milky Way itself might be one of countless similar systems scattered throughout space. Each level of organization suggested underlying physical processes operating on increasingly vast scales of space and time. Greatest challenge facing 18th century astronomy was the fundamental question of cosmic scale. How far away were the stars? How large was the universe? Without distance measurements, All other astronomical quantities remained uncertain. A star's apparent brightness depended both on its intrinsic luminosity and its distance from Earth. Its proper motion through space could indicate either nearby motion at low velocity or distant motion at tremendous speed. The quest for stellar distances drove astronomers to push observational techniques to their limits and beyond. The parallax method, measuring the tiny apparent shift in stellar position as Earth orbited the Sun, offered the most direct approach to distance determination, but required precision measurements at the very edge of technological possibility. James Bradley's discovery of stellar aberration in 1728 provided the first observational proof of Earth's orbital motion around the Sun. But the phenomenon also revealed why parallax measurements were so difficult. The aberration effect, caused by the combination of starlight and Earth's orbital velocity, was thousands of times larger than the parallax shifts astronomers sought to measure. Detecting parallax required separating incredibly small geometric effects from much larger, but well-understood optical phenomena. Technical challenges were daunting. Telescope mounts had to be stable enough to maintain pointing accuracy over hours of observation. Optical systems needed to be free from distortions that might mimic parallax effects, atmospheric turbulence, temperature variations, and instrumental flexure, all introduced errors that could mask the tiny signals astronomers sought to detect. The problem of stellar distances carried implications far beyond technical astronomy. If the stars were truly at vast distances, as the failure to detect parallax suggested, then their apparent brightness implied intrinsic luminosities far exceeding that of the Sun stars would be revealed not as mere points of light but as blazing suns, perhaps accompanied by their own planetary systems and possibly their own forms of life. The possibility of other worlds orbiting distant stars captured the imagination of philosophers and natural theologians. If the universe contained countless stars, and if these stars were suns like our own, then the cosmos might teem with life on scales previously unimaginable. The theological implications were profound. A universe filled with inhabited worlds suggested a deity of infinite creativity and benevolence, yet also raised troubling questions about humanity's unique status in creation. Some astronomers attempted indirect approaches to distance measurement. If all stars had approximately the same intrinsic brightness as the Sun, then their apparent brightnesses could indicate their relative distances. This assumption, though crude, suggested that even the brightest stars lay at distances hundreds of times greater than the size of Earth's orbit around the Sun. Statistical approach to stellar distances yielded another startling insight. If stars were distributed more or less uniformly through space, then their apparent brightness distribution should follow predictable patterns. Observations showed that faint stars vastly outnumbered bright ones, exactly as expected if brightness decreased with distance. The stellar census supported the hypothesis of a vast, three-dimensional stellar system extending far beyond the solar neighborhood. William Herschel attempted to map the three-dimensional structure of the stellar system using star counts in different directions. His star gauging revealed that the Milky Way represented not a distant nebulous cloud, but the plane of the stellar system as seen from within. Humanity, Herschel realized, lived inside a vast flattened collection of stars, seeing the system edge on as the luminous band of the cosmos Milky Way stretching across the night sky. By the close of the 18th century, astronomy had achieved a remarkable synthesis of observation and theory. Newton's gravitational framework provided the mathematical foundation for understanding celestial motions. Increasingly sophisticated observations revealed the complexity and scale of the stellar universe. The combination of theoretical understanding and observational capability created a new vision of the cosmos as a vast, interconnected system governed by comprehensible natural laws. Pierre-Simon Laplace, the great French mathematician and astronomer, captured this vision in his influential treatise on celestial mechanics. Laplace demonstrated that the apparent irregularities in planetary motion, the source of so much concern for earlier astronomers, could be explained as the inevitable result of gravitational interactions between solar system bodies. The universe, he showed, was indeed a clockwork, but one of such complexity and precision that its ultimate behavior could be predicted with mathematical certainty. Laplace's confidence in the power of mathematical analysis led him to formulate what became known as Laplacian determinism, the idea that if the position and velocity of every particle in the universe were known at any given moment, the entire future and past history of the cosmos could be calculated. This vision of complete cosmic predictability represented the ultimate triumph of the mechanistic worldview over the capricious gods and mysterious forces that had dominated earlier cosmology. Even as Laplace celebrated the triumph of mathematical astronomy, new observations were revealing phenomena that challenged the limits of mechanistic explanation. The discovery of stellar proper motion had shown that stars moved through space, but what forces governed their motion? Gravitational attraction between neighboring stars seemed too weak to account for the observed motions. Yet no other force was known that could act across the vast distances of interstellar space. The problem of stellar dynamics pointed toward a fundamental limitation of the Newtonian synthesis. While Newton's laws could predict the motion of planets with exquisite precision, they seemed inadequate to explain the large-scale structure and evolution of the stellar universe. Stars appeared to be organized into complex systems, double stars, star clusters, the Milky Way itself, but the forces responsible for this organization remained mysterious. Some astronomers began to suspect that the stellar universe might be evolving over timescales far longer than human history. If stars move through space under gravitational influence, then the configuration of the stellar system must change over cosmic time. Star clusters might condense from initially dispersed distributions. The Milky Way itself might be slowly rotating, carrying its component stars in great orbital cycles, lasting millions of years. The possibility of cosmic evolution introduced a temporal dimension to astronomy that had been largely absent from earlier investigations. The stars, previously seen as eternal and unchanging, might be born, evolve, and eventually die over cosmic timescales. The universe itself might have a history with a beginning, middle, and perhaps an end determined by the inexorable operation of natural laws. This evolutionary perspective raised profound questions about the nature of time and change in the cosmos. If the universe had evolved from some initial configuration, what had determined that configuration? If cosmic evolution would continue into the future, what would be the ultimate fate of stars, planets, and any life they might harbor? The theological implications of cosmic evolution proved as challenging as its scientific aspects. Traditional natural theology had found evidence of divine design in the apparent perfection and stability of celestial motions. If the universe was actually evolving, if its current state was temporary rather than eternal, then divine action might be required to maintain cosmic order over time. Or alternatively, the universe might be running down toward some final state of maximum entropy and minimum order. As the 19th century dawned, astronomy stood at a crossroads between the mathematical precision of celestial mechanics, and the observational richness revealed by increasingly powerful telescopes. The success of Newton's gravitational theory in explaining planetary motions had demonstrated the power of mathematical physics to unlock cosmic secrets. Yet the stars themselves remained largely mysterious. Their distances, sizes, masses, and physical compositions were still unknown, making them little more than mathematical points in the equations of stellar dynamics. The development of new observational techniques promised to bridge this gap between mathematical astronomy and physical understanding. Improvements in telescope design and optical theory made possible observations of unprecedented precision and detail. More importantly, entirely new types of astronomical observation were becoming possible, opening windows into aspects of stellar nature that had previously been inaccessible to investigation. First successful measurement of stellar parallax, achieved almost simultaneously by Friedrich Bessel, Thomas Henderson, and Friedrich Struve in the 1830s, marked a turning point in humanity's understanding of cosmic scale. Bessel's measurement of the parallax of 61 Cygni revealed that even this relatively nearby star lay at a distance of more than 11 light-years from Earth. The measurement confirmed what astronomers had long suspected. The stars were indeed at distances so vast that light itself, traveling at 186,000 miles per second, required years to cross the space between stars and Earth. The implications of stellar distance measurements transformed astronomy from a study of apparent celestial motions to an investigation of the physical universe itself. If stars were at distances of light years, then their apparent brightness implied intrinsic luminosities comparable to or exceeding that of the sun. The stars were revealed as suns, blazing with nuclear fires and probably accompanied by their own retinues of planets and moons. More profoundly, the measurement of stellar distances revealed that light carried information, not just about the present state of the universe, but about its past. The light from 61 Cygni that Bessel analyzed in his parallax measurements had left that star more than 11 years earlier. When astronomers looked at the stars, they were seeing not the universe as it existed in their present moment, but as it had existed in the past, with more distant objects appearing as they had been at increasingly remote times. This revelation answered the question that would later be posed in the title of our story: why do we see stars as they were, not as they are? The answer lay in the finite speed of light and the vast distances between stars. Light from distant objects must travel across space to reach Earth, and this travel time means that astronomical observations always provide information about the past state of the universe rather than its present condition. The concept of look-back time in astronomical observation introduced a new dimension to cosmic understanding. Every telescope became a time machine, allowing astronomers to observe the universe at different epochs by looking at objects at different distances. The most distant observable objects would appear as they existed in the remote past, potentially revealing information about the early history and evolution of the cosmos itself. This temporal aspect of astronomical observation suggested that the universe possessed a history, that its current state resulted from long processes of change and evolution stretching back into the distant past. The stars might not be eternal and unchanging, as ancient astronomers had believed, but temporary structures formed through natural processes and destined to evolve and eventually disappear over cosmic time scales. Recognition that stellar light carried information about the past state of the universe opened new avenues for astronomical investigation. If different stars had formed at different times in cosmic history, Then observations of stars at various distances might reveal the sequence of stellar formation and evolution. The universe itself might be readable as a vast library of information about its own history, with each star serving as a chapter in the cosmic story. As the 19th century progressed, new observational techniques would make possible increasingly detailed studies of stellar properties and behavior. The development of stellar spectroscopy would reveal the chemical composition of stars and provide insights into the physical processes powering their luminosity. Photography would enable precise measurements of stellar positions and motions, leading to statistical studies of stellar populations and galactic structure. Yet even as these new techniques were being developed, the fundamental insight of the early 19th century remained central to astronomical understanding. The universe was vast, ancient, and evolving, and human beings observed it not as it was, but as it had been at various times in its long history. This perspective would prove essential to the development of modern cosmology and the eventual recognition that the universe itself had a beginning, an evolution, and perhaps an ultimate fate determined by the operation of natural laws on the grandest possible scale. Journey from ancient stargazing to this new understanding of cosmic history represented one of the greatest intellectual achievements in human history. Through patient observation, mathematical analysis, and theoretical insight, astronomers had transformed the night sky from a collection of mysterious lights into windows opening onto the deep structure and evolution of reality itself. The stars, once seen as eternal and unchanging, were revealed as dynamic actors in a cosmic drama spanning billions of years and countless worlds, and this transformation was still in its earliest stages. The 19th and 20th centuries would bring discoveries that would dwarf even the 20th centuries, revolutionary insights of the Newtonian era, the nature of stellar energy, the structure of galaxies, the expansion of the universe, and the cosmic background radiation would all contribute to an understanding of the cosmos that made even Laplace's mechanistic universe seem small and simple by comparison. The story of stars was also the story of human curiosity and determination, of the gradual expansion of knowledge and understanding that had carried humanity from Earth-centered cosmology to its place in an evolving universe of unimaginable scale and complexity. Yet as this great intellectual adventure continued, the fundamental questions that had driven the earliest astronomers remained as compelling as ever. What was humanity's place in the cosmic order? How had the universe come to be as it was? What did the future hold for stars, planets, and the life they harbored? The answers to these questions would require new types of observation, new theoretical frameworks, and new ways of thinking about the nature of space, time, and matter itself. The age of classical astronomy was drawing to a close, but the age of modern astrophysics was just beginning. The stars that had first stirred human wonder in the dark nights of prehistory were about to reveal secrets that would transform not only scientific understanding, but the very conception of what it meant to be human in an infinite universe governed by mathematical laws, yet filled with mystery and beauty beyond all imagination. 20th century arrived like a gentle tide, carrying with it minds that would reshape humanity's understanding of the cosmos in ways that earlier astronomers could never have imagined. In quiet studies and bustling laboratories, new voices began to whisper questions that would become thunderous revelations. The stars, those ancient beacons that had guided sailors and inspired poets, were about to reveal secrets that would humble and elevate the human spirit in equal measure. In the early years of the 1900s, as horse-drawn carriages still shared streets with the first automobiles. A young patent examiner named Albert Einstein sat in his modest office in Bern, Switzerland. His desk was cluttered with applications for new inventions, but his mind wandered far beyond the mechanical contraptions described in the papers before him. He gazed through his window at the Alps, their snow-capped peaks catching the morning light, and pondered the nature of light itself. Einstein had been troubled by questions that seemed to exist at the very edges of human understanding. If light was a wave, as many believed, then what medium did it travel through? The luminiferous ether, that hypothetical substance that supposedly filled all of space, had never been detected despite the most careful experiments. And what happened when objects moved at tremendous speeds, approaching the velocity of light itself? In 1905, this quiet clerk published a series of papers that would forever change how humanity understood the universe. His special theory of relativity proposed something revolutionary. Space and time were not separate, immutable entities, but rather a unified fabric that could be stretched, compressed, and warped. The speed of light, he declared, was constant for all observers, regardless of their motion. This simple statement carried profound implications that rippled through the foundations of physics like stones thrown into a still pond. But it was Einstein's later work, his general theory of relativity published in 1915, that would truly transform our understanding of the cosmos. He proposed that massive objects actually curved the fabric of spacetime itself, creating what we experience as gravity. The sun did not pull the Earth toward it through some mysterious force acting across empty space. Rather, the sun's enormous mass created a depression in spacetime, and the Earth simply followed the curved path around this cosmic valley. This insight had staggering implications for the star's light. Einstein realized would follow these curves in spacetime. When starlight traveled across the vast distances of the universe, it would be bent and redirected by the gravitational fields of massive objects. More significantly, as light climbed out of gravitational wells, it would lose energy, becoming redder. This gravitational redshift would join the Doppler effect as another reason why distant stars might appear different from their true nature. Meanwhile, across the Atlantic Ocean, another revolution was quietly unfolding in the clear mountain air of California. Mount Wilson Observatory, perched high above the Los Angeles basin, had become home to the largest telescope in the world. The 100-inch Hooker telescope, completed in 1917, gathered light with an unprecedented hunger, pulling faint whispers from the deepest reaches of space and transforming them into photographs that would rewrite astronomy textbooks. Working with this magnificent instrument was Edwin Hubble, a man whose patient observations would reveal the true scale of the universe. Hubble had originally studied law, following his father's wishes, but the call of the stars proved irresistible. He spent his nights at the telescope, carefully photographing spiral nebulae, those fuzzy, ethereal objects that had puzzled astronomers for generations. Question that haunted Hubble was whether these spiral nebulae were relatively nearby objects within our own Milky Way, or whether they might be separate galaxies, entire stellar cities containing billions of stars, scattered across incomprehensible distances. To answer this question, he needed to measure distances with unprecedented precision night after night. Hubble scrutinized the spiral nebula in Andromeda, searching for variable stars that could serve as cosmic lighthouses. In 1924, his persistence was rewarded when he identified several Cepheid variables within the Andromeda Nebula using Henrietta Leavitt's period luminosity relationship. He calculated that these stars were incredibly distant, far beyond the boundaries of the Milky Way. The revelation struck the astronomical community like lightning illuminating a vast landscape previously hidden in darkness. The Andromeda Nebula was not a nearby cloud of gas and dust, but an entire galaxy containing hundreds of billions of stars. Located more than 2 million light-years away, in an instant, the known universe expanded beyond all previous imagination. Humanity suddenly found itself inhabiting not just one galaxy among countless others, but a cosmos so vast that even light, the fastest messenger in the universe, required millions of years to traverse the distances between these island universes. But Hubble's discoveries had only begun to reshape our understanding of the cosmos. As he continued his observations throughout the 1920s, he noticed something peculiar about the light from distant galaxies. Their spectra were systematically shifted toward longer, redder wavelengths. The more distant a galaxy appeared, the greater its redshift seemed to be. This pattern suggested something extraordinary. The universe itself was expanding, carrying galaxies away from each other like raisins in rising bread. Though the redshift was not primarily due to the galaxies moving through space, but rather to the expansion of space itself, stretching the wavelengths of light as they traveled across cosmic distances. Hubble's observations provided the first concrete evidence for what would become known as the Big Bang Theory. If the universe was expanding now than in the distant past, everything must have been much closer together. Tracing this expansion backward in time led to a moment of incredible density and temperature, a close to cosmic beginning when time and space themselves emerged from a singularity smaller than an atom. Implications for understanding starlight were profound. Every photon that reached Earth from a distant star or galaxy had been traveling for years, decades, centuries, or millennia. During its journey, the universe had been expanding, stretching space itself and carrying the source of the light ever further away. By the time the light reached Earth, the star or galaxy that emitted it might have changed dramatically, aged significantly, or even died entirely. This realization answered the fundamental question that had inspired this cosmic journey. We see stars as they were, not as they are, because light has a finite speed, and the universe is both vast and ancient. A star that appears to shine peacefully in tonight's sky might have exploded in a violent supernova years ago, but its final light has not yet had time to reach us. We live in a universe where the present moment is unknowable at cosmic distances, where we are forever looking backward through time whenever we gaze upward at the stars. As the 20th century progressed, astronomers began to grasp the full implications of living in an expanding universe filled with light that carries messages from the past. The concept of look-back time became central to astronomical thinking. When we observe a star that is 100 light-years away, we see it as it existed 100 years ago. A galaxy located 10 billion light-years distant appears to us as it was when the universe was less than a quarter of its current age. This temporal architecture of observation meant that astronomers were not just mapping space, but also traveling through time. The deeper they looked into the cosmos, the further back in cosmic history they could peer. The most distant objects visible to telescopes appeared as they existed when the universe was young, when the first stars were forming and the first galaxies were condensing from primordial hydrogen and helium. Einstein's theories provided the mathematical framework for understanding this cosmic time machine. His equations revealed that space and time were intimately connected, forming a four-dimensional continuum that could be warped by matter and energy. Massive objects created gravitational wells in this space-time fabric, and these wells affected not just the paths that objects followed, but also the flow of time. itself near a massive star, time would flow more slowly relative to an observer far from any gravitational influence. This gravitational time dilation meant that starlight carried within it a record not just of when it was emitted, what elements were present, and how fast the source was moving, but also information about the gravitational environment in which it originated. The work of astronomers like Hubble, combined with Einstein's insights, revealed that the universe was far more dynamic and interconnected than anyone had previously imagined. Stars were not simply distant suns burning in empty space, but participants in a vast cosmic dance that involved the expansion of space itself, the evolution of matter from simple to complex, and the flow of time at different rates depending on gravitational conditions. In the 1940s and 1950s, new discoveries continued to deepen our understanding of stellar light and cosmic time. Radio astronomy, which detected invisible radiation from celestial objects, revealed phenomena that were completely hidden from optical observation. Pulsars rapidly spinning neutron stars sent out beams of radio waves like cosmic lighthouses, their precise timing providing insights into the nature of matter under extreme conditions. The development of nuclear physics also illuminated the source of stellar energy. Scientists finally understood that stars were not burning like enormous campfires, but rather fusing hydrogen into helium in their cores, converting tiny amounts of matter into tremendous quantities of energy, according to Einstein's famous equation, E equals mc. This process of stellar nucleosynthesis explained not only how stars could shine for billions of years, but also how the heavier elements essential for life were forged in stellar cores and distributed throughout the universe when massive stars exploded as supernova. As the space age dawned in the late 20th century, humanity's ability to study starlight took a revolutionary leap forward. Telescopes placed above Earth's atmosphere could observe wavelengths of electromagnetic radiation that never reached the ground. Ultraviolet light, X-rays, and infrared radiation that reveal different aspects of stellar behavior and cosmic phenomena. The Hubble Space Telescope, launched in 1990 and named after the pioneering astronomer, became humanity's most famous eye on the cosmos, free from the blurring effects of Earth's atmosphere. Hubble could resolve details in distant galaxies with unprecedented clarity. Its images revealed the universe to be even more beautiful and complex than anyone had imagined. Filled with stellar nurseries where new stars were born, planetary nebulae, where dying stars shed their outer layers in colorful displays, and ancient galaxies that existed when the universe was young. Each photograph from Hubble and other space telescopes served as a time machine, capturing light that had traveled for millions or billions of years to reach the telescope's mirrors. The deepest images, obtained by pointing telescopes at seemingly empty patches of sky for hours or days, revealed galaxies so distant that their light had been traveling since shortly after the Big Bang. These deep field images showed the universe as it appeared when it was less than 1 billion years old, populated by smaller, more irregular galaxies, quite different from the mature spiral and elliptical galaxies we see in the nearby universe today. The realization that we see cosmic objects as they were, not as they are, became more than just an interesting scientific fact. It became a profound meditation on the nature of knowledge itself. Every observation of the cosmos is simultaneously an observation of the past. The present state of distant objects remains fundamentally unknowable until their light has time to reach us. We are all cosmic archaeologists, piecing together the history of the universe from the ancient light that reaches our eyes and instruments. This temporal separation also means that the stars we see tonight may no longer exist. The bright star Rigel in the constellation Orion is approximately 860 light-years away. So we see it as it appeared during the Middle Ages on Earth. If Rigel exploded in a supernova tomorrow, we would not know about this catastrophic event until the year 2884. The star could vanish from existence, and we would continue to see it shining peacefully in the winter sky for nearly 9 more centuries. Conversely, new stars may have formed in distant regions of our galaxy centuries ago, but their light has not yet had time to reach us. The night sky we see is not a snapshot of the current state of the cosmos, but rather a complex layering of light from different epochs, each photon carrying its own timestamp from the moment it was emitted. Modern astronomy has revealed that this temporal separation applies not just to individual stars, but to cosmic phenomena on all scales. The cosmic microwave, background radiation, the afterglow of the Big Bang itself, shows us the universe as it appeared 380,000 years after its birth. When it first became transparent to light, this ancient radiation still fills all of space, carrying information about the early universe that continues to inform our understanding of cosmic evolution as the 21st century began. New generations of telescopes and space missions continued to refine our understanding of cosmic time. And the journey of starlight, the Spitzer Space Telescope, revealed the infrared universe, showing how dust and gas between stars affected the light passing through it. The Kepler Space Telescope monitored thousands of stars simultaneously, detecting the tiny dimming that occurs when planets pass in front of their host stars, revealing that planetary systems are common throughout the galaxy. Each of these discoveries reinforced the fundamental truth that observation and time are inextricably linked in astronomy. When Kepler detected the transit of an exoplanet around a star 1,000 light-years away, it was observing an event that actually occurred during the time of the medieval period on Earth. If intelligent beings exist on that distant world, they might at this very moment be receiving light from our sun that shows Earth as it appeared 1,000 years ago, perhaps wondering about the possibilities for life on this small blue planet orbiting an ordinary yellow star. The concept of simultaneity, which seems so obvious in our daily experience, becomes meaningless on cosmic scales. There is no universal now that applies throughout the universe. Events that we consider simultaneous may have actually occurred millions of years apart, when we account for the time it takes light to travel between distant locations. Einstein's relativity theories also revealed that the passage of time itself depends on motion and gravity. Astronauts orbiting Earth at high speeds experience time slightly differently than people on the surface. If we could somehow travel at velocities approaching the speed of light toward a distant star, we would experience time dilation. Our clocks would run slower relative to those left behind on Earth. This means that even the concept of when a distant star appears depends on the reference frame of the observer. These insights have transformed astronomy from a science that simply catalogues celestial objects to one that studies the evolution of the universe through time. Modern astronomers are temporal explorers, using the finite speed of light to observe cosmic history directly. They can watch galaxies collide in slow motion over millions of years, trace the life cycles of stars from birth to death, and study how the large-scale structure of the universe has evolved since the Big Bang. Atacama Large Millimeter Array, ALMA, in Chile can observe the radio waves emitted by molecular clouds, where stars are forming, revealing these stellar nurseries as they existed millions of years ago. The James Webb Space Telescope, launched in 2021, can peer even deeper into space and time, observing the first galaxies that formed when the universe was less than 500 million years old. Each new observation adds another piece to our understanding of cosmic evolution and the journey of light through space and time. This temporal perspective has also changed how we think about our place in the cosmos. We exist at a specific moment in cosmic history, approximately 138 billion years after the Big Bang. The stars we see in tonight's sky represent light emitted at various points in this vast timeline, creating a three-dimensional map of space that is also a four-dimensional map of space-time. There is something profoundly poetic about the realization that we see stars as they were, not as they are. This simple fact connects us intimately with the cosmic past, making every glance at the night sky a form of time travel. The light that enters our eyes left distant stars years, decades, or centuries ago, carrying with it information about conditions that existed long before we were born. When we look at the constellation Orion on a winter evening, we are seeing a collection of stars at vastly different distances, their light having left them at different times in human history. The bright star Betelgeuse, which forms Orion's shoulder, is about 650 light-years away, so we see it as it appeared during the late medieval period. The star Mintaka in Orion's belt is approximately 900 light-years distant, showing us light that began its journey during the early Middle Ages. These stars appear to form a coherent pattern in our sky, but this is purely an illusion created by our perspective from Earth. In reality, they exist at different distances and different points in time as we observe them. The constellation patterns that have guided human navigation and inspired mythology for thousands of years are temporal collages, combining light from different epochs of cosmic history. This temporal mixing extends to our understanding of stellar evolution as well. When we observe stars of different masses and ages scattered throughout our galaxy, we are essentially seeing snapshots of stellar evolution, frozen at different stages. A massive, young blue star shows us what conditions were like shortly after star formation began in a particular region. An ancient red giant reveals the fate that awaits stars like our Sun billions of years in the future. The white dwarf remnants of long-dead stars tell us about stellar death and the recycling of matter through the cosmos. Modern astrophotography has made these temporal relationships visible in spectacular ways. Images of star-forming regions like the Eagle Nebula show pillars of gas and dust where new stars are being born, their light having taken thousands of years to reach us. These stellar nurseries appear to us as they existed during the height of human civilization. Yet the star formation process we observe unfolding is the same one that created our own sun. Nearly 5 billion years ago, the Hubble Space Telescope's deep-field images have pushed this temporal perspective to its extreme limits. The Hubble Ultra Deep Field, created by combining hundreds of hours of observations of a tiny patch of sky, reveals galaxies as they appeared when the universe was less than 1 billion years old. These ancient galaxies show us cosmic conditions that existed long before our solar system formed, providing direct observational evidence of how the universe has evolved over cosmic time. Each of these distant galaxies contains billions of stars, and the light we receive is the combined glow of all those stellar fires as they burned billions of years ago. Some of those stars may have formed planetary systems and perhaps even harbored life, but any civilizations that might have existed around those stars would have risen and fallen long before Earth even existed. Their light continues to reach us now, like messages from a cosmic past that we can observe, but never directly experience from the photon's perspective. However, the journey across cosmic distances happens instantaneously, according to Einstein's relativity. Objects traveling at the speed of light experience no passage of time. A photon emitted by a star in the Andromeda galaxy begins its journey to Earth 25 million years ago from our perspective. But from the photon's reference frame, it arrives at Earth at the same instant. It was emitted. Light exists in an eternal present, even as it carries information about the past to observers who exist within the flow of time. This paradox highlights one of the most beautiful aspects of our cosmic situation. We are temporal beings observing an eternal phenomenon. Light transcends time while simultaneously being our primary means of measuring and understanding time on cosmic scales. The speed of light serves as both a fundamental constant of nature and the ultimate speed limit of the universe, determining how quickly information can travel from one location to another. Finite speed of light also creates a natural limit to what we can observe in the universe. The observable universe extends only as far as light has had time to travel. Since the Big Bang approximately 138 billion years ago, beyond this cosmic horizon, there may be countless more galaxies and stars. But their light has not yet had time to reach us. This horizon is constantly expanding as the universe ages, gradually revealing new regions of space that were previously beyond our observational reach within this observable universe. Every star, galaxy, and cosmic phenomenon we can detect represents a specific moment in cosmic history. The most distant objects we can observe show us the universe as it appeared when it was young and very different from today. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old and had just become transparent to light for the first time. As we look deeper into space and further back in time, we approach the moment of cosmic dawn, the epoch when the first stars formed and began to illuminate the universe. These earliest stars were different from the stars we see today, composed almost entirely of hydrogen and helium, because heavier elements had not yet been forged in stellar cores. When these massive first stars died in spectacular supernova, they scattered the heavier elements throughout space, enriching the gas from which later generations of stars would form. Our Sun is a third-generation star, formed from gas that had already been enriched by the deaths of earlier stellar generations. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all forged in the cores of ancient stars that died billions of years ago. We are quite literally made of stardust, connected to the cosmic story through the very atoms that compose our being. This connection between starlight and human existence extends beyond mere chemistry. The energy that powers all life on Earth comes from nuclear fusion in the Sun's core, where hydrogen is converted to helium in the same process that lights the stars. Sunlight takes about 8 minutes and 20 seconds to travel from the Sun to Earth, which means the light warming our planet today was created in the solar core and then bounced around through the Sun's interior for thousands of years before finally escaping into space and making its brief journey to our world. As humanity's technological capabilities continue to advance, our ability to study the relationship between light and time on cosmic scales grows ever more sophisticated. The next generation of telescopes will push the boundaries of observation even further, allowing us to see deeper into space and further back in cosmic time than ever before. The James Webb Space Telescope represents a quantum leap in our ability to observe the early universe. Its large primary mirror and advanced infrared instruments can detect the stretched light from the most distant galaxies, revealing cosmic conditions when the universe was less than 400 million years old. These observations will help us understand how the first stars and galaxies formed, and how they influenced the evolution of the cosmos' future. Space missions will continue to refine our understanding of cosmic time and the journey of light. Proposed telescopes with even larger mirrors and more sensitive detectors will be able to study individual stars and distant galaxies, observing stellar populations as they existed billions of years ago. These observations will allow astronomers to trace the chemical evolution of the universe with unprecedented detail, watching how the abundance of heavy elements gradually increased as successive generations of stars lived and died. The search for life beyond Earth is also intimately connected to our understanding of light and time. When astronomers discover potentially habitable exoplanets around distant stars, they are observing worlds as they existed years or decades ago when their light began its journey to Earth. If we ever detect signs of life in the atmospheres of these distant worlds, perhaps through the spectroscopic detection of oxygen or other biosignatures, we will be observing life as it existed in the past, not as it might exist today. This temporal separation means that any communication with potential extraterrestrial civilizations would be a very slow process. A radio message sent to a star system 100 light-years away would take 100 years to arrive, and any response would take another 100 years to return to Earth. Conversations between civilizations separated by cosmic distances would unfold over centuries or millennia, with each participant responding to messages that were already decades or centuries old by the time they arrived. Study of gravitational waves ripples in spacetime, itself detected by instruments like LIGO, has opened a new window for observing cosmic events. When two black holes merge billions of light years away, they create gravitational waves that travel at the speed of light, carrying information about these violent events across the cosmos. These waves arrive at Earth billions of years after the original collision, providing another way to study the universe as it existed in the distant past. Gravitational wave astronomy represents a new form of cosmic archaeology, allowing us to study events that produce no electromagnetic radiation, but dramatically warp spacetime itself. The merger of neutron stars can be observed both through gravitational waves and through the electromagnetic radiation produced in the collision, providing multiple perspectives on the same ancient cosmic event. As our understanding of cosmic time and the journey of starlight has deepened, the original question, why do we see stars as they were, not as they are, has revealed layers of meaning that extend far beyond simple physics. This question touches on fundamental aspects of knowledge, reality, and our place in the universe that philosophers and scientists continue to explore. The finite speed of light means that all observation involves looking into the past. Even when we look at objects in our immediate surroundings, we are seeing them as they appeared nanoseconds ago when light reflected from them and entered our eyes. This temporal separation is usually negligible for everyday experience, but it becomes profound when we consider cosmic distances on cosmic scales. This temporal separation raises deep questions about the nature of reality itself. If we can never observe the present state of distant objects, what does it mean to say that those objects exist now? The present moment, which seems so immediate and real in our daily experience, becomes ambiguous and relative when we consider the universe as a whole. Einstein's theories revealed that simultaneity is not absolute, but depends on the reference frame of the observer. Events that appear simultaneous to one observer may occur at different times according to another observer, moving at high speed relative to the first. This relativity of simultaneity means that there is no universal now that applies throughout the universe. Different observers will disagree about whether distant events are happening now or in the past or future. These insights have profound implications for our understanding of cosmic evolution and the fate of the universe. When we observe distant galaxies moving away from us due to the expansion of space, we are seeing them as they were billions of years ago. The current state of these galaxies remains unknown to us, and may indeed be unknowable if the expansion of space eventually carries them beyond our observational horizon. The accelerating expansion of the universe, driven by dark energy, means that distant galaxies are receding from us at ever-increasing speeds. Eventually, galaxies beyond our local group will disappear from view as their light becomes too redshifted to detect. Future astronomers living trillions of years from now will inhabit a universe that appears much emptier and more isolated than the cosmos we observe today. Yet even as the observable universe may eventually shrink due to cosmic expansion, the fundamental relationship between light and time will remain unchanged. Light will continue to travel at its constant speed, carrying information about the past to any observers who remain to detect it. The stars visible in that distant future will still appear as they were, not as they are, maintaining the temporal separation that has characterized cosmic observation since the first light began its journey through space. This temporal aspect of starlight has inspired not only scientific discovery, but also philosophical reflection and artistic expression. Poets have long been moved by the idea that starlight connects us to the cosmic past, that the photons entering our eyes tonight began their journey years or centuries ago. Visual artists have sought to capture the beauty of this temporal connection, creating works that celebrate both the immediacy of stellar beauty and the vast timescales over which that beauty unfolds. Musicians have composed symphonies inspired by the cosmic dance of light and time, attempting to translate the grand rhythms of stellar evolution and cosmic expansion into sound. Writers have crafted stories that explore the implications of living in a universe where observation necessarily involves looking backward through time, where the present state of distant worlds remains forever beyond direct experience. Scientific understanding of why we see stars as they were, not as they are, has thus become woven into human culture in countless ways. This knowledge has changed not only how we understand the cosmos, but also how we see ourselves within it. We are temporal beings living in an ancient universe, connected to cosmic history through the light that reaches our eyes from distant stars and galaxies. Every time we look up at the night sky, we become time travelers, our vision reaching across the years and decades and centuries to touch the cosmic past. The present moment of stellar existence remains beyond our direct experience, hidden behind the fundamental speed limit of the universe. We can only know the stars as they were when their light began its long journey toward Earth, carrying within each photon a message from the cosmic past that continues to shape our understanding of the universe and our place within it. In the end, the answer to why we see stars as they were, not as they are, reveals one of the most beautiful truths about the cosmos: that observation and time are forever intertwined, that distance and duration are inseparable, and that every glance at the heavens is simultaneously an act of seeing and an act of remembering. The stars shine not just across space, but across time itself, their ancient light bridging the vast temporal gulfs that separate us from the cosmic events we observe. And so the stars continue their eternal dance, appearing to us as they were in ages past, their present state remaining a mystery hidden behind the horizon of light speed and cosmic distance. We see them through the lens of time itself. Their beauty filtered through the vast expanses of space and the patient journey of light. In this temporal separation lies perhaps the most profound poetry of all, that in looking outward to the stars, we are also looking backward through time, forever connected to the cosmic past by the simple, elegant fact that light travels at a finite speed through the vast cathedral of space and time. Question that began this journey: why do we see stars as they were, not as they are, has led us through the entire history of human understanding about the cosmos, from ancient stargazers who first noticed the patterns in the sky, to modern astronomers who peer billions of years into the past. With space telescopes, humanity has gradually come to understand that we live in a universe where observation inevitably involves looking backward through time. This understanding has not diminished the wonder of stargazing, but has instead deepened it immeasurably. When we look up at the night sky now, we see not just beautiful points of light, but messengers from the cosmic past. Each star, a time capsule that has traveled across the years to reach our eyes. The simple act of stargazing becomes a profound meditation on time, distance, and the nature of reality itself. The stars appear to us as they were, not as they are. Because light, the fundamental messenger between us and the cosmos, travels at a finite speed through the vast expanses of space. This simple fact connects us intimately with cosmic history, while simultaneously highlighting the limits of what we can know about the present state of the universe beyond our immediate vicinity. In embracing this limitation, we discover that it is not a weakness but a profound source of connection to the cosmos. Every photon that enters our eyes carries within it information about when and where it was created, linking us directly to stellar cores, galactic collisions, and cosmic events that occurred long before human civilization began. We are all cosmic archaeologists, using ancient light to piece together the history of the universe and our place within it as we continue to build more powerful telescopes and develop new ways of studying the cosmos. This fundamental relationship between light and time will remain at the heart of astronomy. Future discoveries will undoubtedly reveal new aspects of cosmic evolution and stellar behavior, but they will all be based on the same principle, that light carries information about the past across the vast distances of space, allowing us to witness cosmic history directly through careful observation. The stars shine across time as well as space, their light a bridge between past and present, between the cosmic events that created the elements in our bodies and the moment when we lift our eyes to the night sky in wonder. In seeing stars as they were, not as they are, we participate in one of the most beautiful aspects of existence. In this universe, the eternal dialogue between light and time, between distance and duration, between the cosmic past and the eternal human desire to understand our place among the stars. So the ancient light continues its journey, carrying messages from cosmic fires that burned millions of years ago, reaching across the vast emptiness of space to touch our eyes and kindle our imagination. In that touch of ancient starlight on human vision lies the answer to our question, and the beginning of countless new mysteries yet to be explored. The stars appear to us as they were because light itself is the messenger of time, and in receiving that message, we become participants in the grand cosmic story that began with the Big Bang and continues to unfold around us every night. When we turn our faces toward the infinite star-filled sky, the cosmic dance continues, measured not in seconds or minutes, but in the patient journey of light across astronomical distances, in the slow evolution of stars from birth to death, and in the gradual expansion of space itself. We are privileged to witness this dance, to receive the ancient light of stars, and to understand perhaps for the first time in cosmic history why we see the universe as it was, not as it is. In that understanding lies both humility and wonder, both the recognition of our limitations and the celebration of our remarkable ability to peer backward through time and space to touch the very origins of the cosmos itself. Time flows onward, carrying us all toward an uncertain future, but the stars remain as they have always been, beacons in the darkness, messengers from the past, reminders of the vast scales of space and time that dwarf human experience, yet somehow manage to inspire and humble us in equal measure. They shine as they were, not as they are. And in that simple fact lies perhaps the most beautiful truth about our place in the universe, that we are connected to the cosmic past by threads of light that stretch across unimaginable distances, binding us to the stars themselves through the patient, eternal journey of photons across the void in the end. Beneath the layers of time and across the gulfs of space, only the light remains ancient, patient, eternal. It whispers to us of stellar births in distant nebulae, of the slow dance of galaxies across cosmic epochs, of the fundamental forces that shape reality itself. This light carries the past into the present, the distant into the immediate, the cosmic into the personal, and in receiving this gift of ancient starlight, we become part of the story it tells, temporary observers in an eternal cosmic narrative that began with the first stars and will continue long after the last one has faded into darkness. The stars shine on, appearing to us as they were in ages past, their present state forever hidden behind the horizon of light and time. Yet in that temporal separation lies not loss but connection, not ignorance but the deepest possible intimacy with cosmic history. Every glance at the night sky is a journey through time, every star a window into the past, every photon a messenger from the depths of space and the beginning of time itself. And so we see the stars as they were, not as they are, and in doing so we touch the eternal mystery that lies at the heart of existence in this vast, ancient, ever-expanding universe of light and time and wonder. Thank you for joining us on this journey through the history of humanity's quest to understand the stars. If these timeless stories have moved you, please take a moment to like, share, and subscribe. To fall asleep to history, let these ancient tales of wonder and discovery find new hearts, just like yours. Sweet dreams await among the stars. Subscribe for more journeys through history.